Hello and welcome. Tonight we're going to explore something so familiar yet so profoundly misunderstood that it took humanity thousands of years to begin grasping its true nature. Something that touches every moment of your existence yet remains invisible to your senses. Right now, as you lie here listening, you're experiencing what most people call gravity pulling you down toward Earth. But here's what might keep you wondering. As you drift toward sleep, gravity isn't pulling you at all. In fact, gravity isn't even a force in the way we've been taught to think about forces. What you're actually feeling is the resistance of your bed pushing up against you as you try to follow the straightest possible path through curved space. Your body wants to move through space-time in a straight line, but Earth's mass has bent that space-time around you, and the ground won't let you follow your natural trajectory. You're not being pulled down, you're being held up. If that sounds strange, beautiful, even a little unsettling, then you're beginning to see what took Einstein a decade of intense work to understand. And if you're curious to discover how this single insight reshapes everything we thought we knew about the universe, about time, about the fate of galaxies themselves, then stay with me. Because by the end of our journey together, you'll never look at a falling leaf or the moon or your own weight on this bed quite the same way again. Before we go further, if you enjoy falling asleep, to science told softly to stories that blend wonder with understanding, I'd be grateful if you'd like this video and subscribe to the channel. It helps more people find these quiet explorations of our universe. And now, let's begin where most gravity stories begin, with an apple and a man sitting beneath a tree. The year was 1666, and Isaac Newton was in his early 20s, sheltering at his family's manor in Lincolnshire during the Great Plague that had closed Cambridge University. The famous story tells us that watching an apple fall inspired his theory of universal gravitation. But what's often left out is this: Newton didn't just wonder why the apple fell, he wondered why the moon didn't fall. Both, he realized, must be subject to the same force. The apple falls from the tree. The moon, in a sense, is constantly falling toward Earth, but moving forward fast enough that it keeps missing. This was revolutionary not because falling was new, but because Newton unified the heavens and Earth under one mathematical law. Newton's law of universal gravitation was elegant, powerful, predictive. It stated that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. For over 200 years, this law explained planetary orbits, predicted the existence of Neptune before it was observed, and became the bedrock of physics and astronomy. But there was something Newton himself admitted troubled him deeply. He wrote in his Principia, "I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses." In other words, I can describe what gravity does, but I cannot tell you what gravity is or how it acts across empty space. This wasn't just philosophical unease. There was a practical problem too. Newton's gravity was instantaneous action at a distance. If the sun suddenly vanished, Earth would immediately fly off into space. But this troubled physicists because it seemed to require information to travel infinitely fast, which conflicted with emerging ideas about the nature of light and electromagnetic fields. Then came Albert Einstein. In 1905, his special theory of relativity showed that nothing, not even information, can travel faster than light. Space and time weren't separate fixed stages on which events played out. They were interwoven into a four-dimensional fabric called space-time, and this fabric had properties that depended on your motion through it. Time dilates, lengths contract, simultaneity becomes relative. But special relativity didn't include gravity. And here's where most people misunderstand what happened next. Einstein didn't set out to fix Newton's gravity because it was wrong in some obvious way. Newton's predictions were astonishingly accurate for everything we could measure at the time. Einstein set out to make gravity compatible with relativity to understand what gravity actually was. And the insight he arrived at after nearly a decade of struggle was so profound that it changed not just physics, but our conception of reality itself. Einstein realized that gravity wasn't a force at all. It was geometry. Mass and energy don't pull on other objects across space. Instead, they curve the fabric of space-time itself, and objects simply follow the straightest possible paths, called geodesics, through that curved space-time. Imagine you and a friend are standing on opposite sides of Earth's equator, both walking straight north. You're walking in perfectly straight lines, not turning left or right. Yet, as you approach the North Pole, you'll find yourselves getting closer together, not because some force is pulling you together, but because the surface of the sphere naturally brings parallel lines together near the poles. The curvature of Earth's surface guides your paths. Space-time curvature works similarly, but in 4 dimensions instead of 2, and involving time as well as space. When you drop a pen, it's not being pulled by an invisible force. It's following the straightest path it can through space-time that's been curved by Earth's mass. You held up by the floor or your bed are actually the one being accelerated, constantly pushed off your natural geodesic path. This is why you feel weight, not because gravity is pulling you, but because the ground is pushing you away from the path you would naturally follow through curved space-time. This might seem like a semantic difference, a philosophical reframing with no practical consequences. But the predictions are dramatically different from Newton's in extreme conditions. And every test we've conducted confirms Einstein's picture over Newton's. One of the most common misconceptions about gravity is that it's a pulling force like a rope tugging objects together. We grow up with phrases like Earth's gravitational pull so ingrained in our language that the alternative seems counterintuitive. But think about this. If gravity were truly a force pulling you down, then floating in space far from any massive objects, you would feel nothing because there would be no forces on you. But in Einstein's view, floating freely in space is when you're following your natural path through space-time. It's only when something prevents you from following that natural path, like the ground beneath your feet, that you feel a force. Astronauts in orbit around Earth are often said to be in zero gravity, but that's misleading. They're in free fall following their natural geodesic path through space-time curved by Earth's mass. They feel weightless because nothing is pushing them off that path. Here's another way to understand this. When you're standing still on Earth's surface, you feel like you're at rest. But in space-time terms, you're being accelerated upward at 9.8 meters per second, squared by the ground beneath you. The ground is constantly pushing you away from the geodesic you would naturally follow, which would take you toward Earth's center. That acceleration is what you perceive as weight. The rubber sheet analogy is often used to illustrate this, and while it has limitations, it's helpful for visualization. Imagine space-time as a stretched rubber sheet. Place a bowling ball in the center representing a massive object like Earth or the Sun. The sheet curves downward around the ball. Now roll a marble across the sheet. If you roll it fast enough at the right angle, it will orbit the bowling ball, not because the ball is pulling the marble with an invisible rope, but because the marble is following the curved surface of the sheet. Roll it too slowly, or aim it directly at the ball and it will spiral inward. This is orbital mechanics in Einstein's universe. But remember, this analogy is imperfect. Real space-time curvature happens in 4 dimensions, not 2, and involves the curvature of time as well as space. In fact, for most everyday situations like objects falling or satellites orbiting Earth, it's the curvature of time, not space, that dominates. Time flows at slightly different rates depending on how deep you are in a gravitational field, and it's this temporal curvature that causes objects to accelerate toward massive bodies. Let's ground this in something tangible. Every day, your smartphone uses GPS to determine your location. GPS relies on a network of satellites orbiting about 20,000 kilometers above Earth. These satellites carry extremely precise atomic clocks, and they continuously broadcast the time along with their position. Your phone receives signals from multiple satellites, notes the tiny time differences in when each signal arrives, and calculates your position based on those differences. But here's the remarkable thing. If the engineers who designed GPS had used only Newton's physics, ignored Einstein's relativity, the system would accumulate errors of about 10 kilometers every single day. Within a week, your GPS would be virtually useless. Why? Two reasons, both stemming from relativity. First, the satellites are moving at about 14,000 kilometers per hour relative to you on the ground. Special relativity tells us that moving clocks tick slower, so the satellite clocks should fall behind clocks on Earth by about 7 microseconds per day. But second, the satellites are higher up in Earth's gravitational field, where space-time is less curved, and general relativity tells us that clocks in weaker gravitational fields tick faster. This effect speeds up the satellite clocks by about 45 microseconds per day. The net result is that satellite clocks run about 38 microseconds fast each day compared to ground clocks. Engineers have to program the satellites to compensate for this, or the position calculations would rapidly become wildly inaccurate. This isn't theoretical physics happening in exotic conditions. This is Einstein's curved space-time, affecting the device in your pocket every time you check your location. You are navigating through curved space-time, and the engineers who built your tools had to account for that curvature. So, when we talk about gravity shaping space and time, we're not speaking metaphorically. We're describing the literal geometry of the universe you inhabit. And this is just the beginning of understanding what gravity truly is. Now you might be wondering if Newton's description of gravity as a force worked so well for centuries, accurately predicting planetary motions and letting us send rockets to the moon. Why does the distinction matter? Why insist that gravity is geometry rather than force? The answer is that the distinction becomes crucial when gravity is strong, when velocities are high, or when we're examining phenomena over cosmic distances and time scales. Near the surface of Earth, with everyday objects moving at ordinary speeds, Newton's equations and Einstein's give nearly identical predictions. The curvature of space-time near Earth is slight, and Newton's approximation works beautifully. But venture near a black hole, watch light, bend around a galaxy, or try to understand the universe's expansion, and Newton's framework simply cannot explain what we observe. Einstein's can. There's also a deeper lesson here about the nature of scientific progress. Newton wasn't wrong. His law of gravitation is still taught, still used by engineers and astronomers when precision to many decimal places isn't required. But Newton's law was incomplete. It described what happened without explaining the underlying reality. Einstein's theory revealed what gravity actually is, not just what it does. And this pattern repeats throughout science. Each generation's complete understanding becomes the next generation's useful approximation, a special case of a deeper truth. As you settle in, tonight consider that you're not resting on a flat Earth beneath a dome of stars. You're lying on a curved surface of space-time, a surface warped by the mass of the planet beneath you. And that warp age is so slight, so gentle here at Earth's surface that you barely notice it. But that same curvature magnified around more massive objects is responsible for the most extreme phenomena in the cosmos. Stars orbiting invisible black holes at thousands of kilometers per second. Galaxies lensing light from even more distant galaxies. Neutron stars spiraling together and colliding in cataclysms that ring space-time itself like a bell. Gravity isn't what pulls the apple down. Gravity is the shape of the universe at that moment, in that place curved by all the mass and energy present. And the apple released from the tree simply follows the contours of that shape, traces the geometry of existence until the ground intervenes. Understanding this reshapes your relationship with weight, with falling with the stars above and the ground below. You're not held to Earth by an invisible tether. You're following the natural geometry of a curved universe. And only the solidity of matter keeps you from pursuing your geodesic path all the way to the planet's core. You're not static. You're in constant acceleration, pressed upward by the atoms in your bed, pushed away from the path you would freely follow. This is what Einstein saw sitting in the patent office in Bern, imagining what a person falling freely off a roof would feel. They would feel no weight, no gravity. because they'd be following their natural path through space-time. It was an insight so simple and so strange that it opened doorways to understanding the universe at its most fundamental level. And now that we've seen what gravity actually is, the invisible sculptor that shapes not through force but through geometry, we can begin to explore exactly how mass accomplishes this curving, how the fabric of space-time responds to the presence of matter and energy, and why some objects barely dimple that fabric, while others warp it so severely that even light cannot escape. That's where we're headed next. We've established that gravity isn't a force pulling objects together, but rather the curvature of space-time itself. But now comes the natural question. How exactly does mass curve space-time? What's the mechanism? And more importantly, how do we know this isn't just beautiful mathematics, but an accurate description of physical reality? The answer lies in light. Light traveling at the fastest speed possible in our universe always takes the shortest path between 2 points. But here's what's extraordinary: when light passes near a massive object, its path bends. Not because the light is being pulled by gravity as if it had weight, but because the shortest path through curved space-time is itself curved. Imagine drawing the shortest line between 2 cities on a globe. That line curves across the surface because the surface itself is curved. Light does the same thing through curved space-time. And this bending of light gave us the first proof that Einstein was right, and that the fabric of the universe could be warped by mass. If you've ever wondered whether a single observation can change the course of human understanding, whether one measurement can overturn centuries of belief, then what happened on May 29, 1919, might fascinate you as you rest here tonight. Because on that day, during a total solar eclipse, a British astronomer named Arthur Eddington stood on the island of Principe, off the coast of West Africa, pointed his telescope at stars near the darkened sun, and confirmed that space-time itself could bend. Before we continue exploring how this experiment worked and what it revealed, if you're finding this journey through curved space-time as captivating as I do, I'd appreciate if you take a moment to like this video and subscribe. It helps these stories reach others who might enjoy exploring the universe's deepest mysteries as they drift towards sleep. The story of Eddington's expedition begins 4 years earlier in 1915, when Einstein published his general theory of relativity. The mathematics was formidable, the concepts radical. Einstein predicted that light from distant stars passing close to the sun would be deflected by 1.75 arc seconds, a tiny angle about the width of a quarter, seen from 2 miles away. But this was twice the deflection that Newton's theory would predict if you treated light as having mass and being pulled by gravity. The difference between these predictions was crucial. One number would vindicate Newton's intuition about gravity as force. The other would confirm Einstein's revolutionary idea that mass warps space-time itself. But there was a problem. Stars near the sun are invisible during the day because the sun's brightness overwhelms them. The only time you can photograph stars close to the sun's position in the sky is during a total solar eclipse, when the moon blocks the sun's direct light. And total solar eclipses don't happen often, and when they do, they're visible only from narrow paths across Earth's surface. Einstein would have to wait for the right eclipse visible from the right location, with the right stars in the right positions. The eclipse of May 29, 1919 was that opportunity. Eddington, despite the tensions following World War I, Britain and Germany, still recovering from years of conflict, led an expedition to test a German physicist's theory. 2 teams were dispatched. Eddington went to Principe. Another team, led by Andrew Crommelin, went to Sobral in Brazil. Both locations lay in the path of totality. The day of the eclipse arrived. In Principe, clouds threatened to ruin everything. Eddington wrote in his journal that as totality approached, clouds still covered the sun. Then, at the crucial moment, they thinned just enough. For a few precious minutes, the moon's shadow darkened. The sky stars appeared near the sun's corona, and Eddington captured photographic plates of the star field. He had to work quickly. Totality lasted only minutes. Each second counted. He took 16 photographs, though clouds marred many of them. Back in England, Eddington developed the plates and measured the star positions with painstaking precision. He compared them to reference photographs of the same stars taken months earlier when the sun was elsewhere in the sky. The stars near the sun's edge in the eclipse photos appeared shifted from their normal positions. Eddington measured the deflection 1.61 arcseconds within the margin of error of Einstein's prediction of 1.75 arcseconds. The Sobral team's results were even closer one. 98 arcseconds. Light had bent. Space-time had curved. Einstein was right. When the results were announced on November 6, 1919, at a joint meeting of the Royal Society and Royal Astronomical Society in London, the chairman called it the most important result obtained in connection with the theory of gravitation since Newton's day. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Overnight, Einstein became the most famous scientist in the world. But more than personal fame, this was confirmation that the universe operated in a way far stranger than anyone had imagined. Think about what this meant. Light, which has no mass, still responds to space-time curvature. It follows geodesics just like massive objects do. The curvature isn't pulling the light. The curvature is the shape of the path itself. And if the sun, with its enormous but not extreme mass, could bend light measurably, what could more massive objects do? Let's quantify this curvature more precisely. The sun's mass is about 2 times 10 to the 30th kilograms, roughly 333,000 times Earth's mass. At the sun's surface, space-time is curved enough that light passing tangent to the edge bends by those 1.75 arcseconds. At Earth's surface, the curvature is much gentler. Light grazing Earth would bend by only about 0.0005 arcseconds, far too small to measure with any telescope from Earth's surface. Earth's mass creates a shallow dimple in space-time. The sun creates a deeper, steeper well. But these are both gentle compared to what more extreme objects can do. Consider a neutron star. These are the collapsed cores of massive stars that have exploded as supernovae objects, with the mass of the sun compressed into a sphere only about 20 kilometers across. The density is staggering. A teaspoon of neutron star matter would weigh about 1 billion tons on Earth. Space-time around a neutron star is warped so severely that light can orbit the star in circles. If you were standing on the surface of a neutron star, which is impossible for many reasons, including the fact that you'd be instantly crushed and incinerated, you could theoretically see the back of your own head, because light from behind you would curve around the star and reach your eyes. And then there are black holes where space-time curvature becomes so extreme that we run out of everyday analogies. At the event horizon of a black hole, space-time is so sharply curved that even light traveling outward at its maximum speed makes no progress away from the black hole. The escape velocity equals the speed of light. Since nothing can exceed light speed, nothing can escape. The fabric of space-time has been warped into a one-way trap. But let's return to phenomena we can observe and measure more directly. One of the most beautiful confirmations of space-time curvature is gravitational lensing. When a massive object like a galaxy or cluster of galaxies lies between us and a more distant object, the foreground mass warps space-time so much that light from the background object takes multiple curved paths around the foreground mass. We see multiple distorted images of the distant object, or sometimes complete rings called Einstein rings. It's as if the universe has placed a giant lens in space, focusing and distorting the light from distant galaxies. The first gravitational lens was discovered in 1979. Astronomers noticed what appeared to be 2 quasars, incredibly bright and distant objects, positioned very close together in the sky, with nearly identical properties, identical spectra, identical brightness variations over time. The odds of 2 separate quasars being so similar and so close seemed impossibly small. Then Dennis Walsh, Bob Carswell, and Ray Wayman realized they were seeing the same quasar twice its light split and bent around an intervening galaxy. Space-time curvature had created a cosmic mirage. Since then, we've discovered thousands of gravitational lenses. Some create multiple images. Others stretch background galaxies into arcs. The most spectacular create complete Einstein rings, where a perfectly aligned background galaxy is smeared into a circle around the lensing foreground galaxy. Each lens is a natural laboratory for studying both the lensing mass and the lensed object. By analyzing the distortions, astronomers can map the distribution of mass in the lensing galaxy, including dark matter that emits no light but still curves space-time. By examining the lensed images, we can study galaxies so distant that we're seeing them as they appeared when the universe was young. One of the most powerful uses of gravitational lensing is to weigh galaxy clusters, the largest gravitationally bound structures in the universe. A cluster might contain thousands of galaxies spanning millions of light years. When we observe background galaxies through a cluster, their images are distorted into arcs. The degree of distortion depends on how much mass is present in the cluster, and crucially, this measurement is sensitive to all mass visible or dark. What we find is astonishing. The visible galaxies, all the stars and glowing gas, we can see account for only about 15% of the total mass. The rest, about 85%, is dark matter and visible material that reveals itself only through its gravitational effect, its curvature of space-time. One of the most striking examples is the Bullet Cluster, two galaxy clusters that collided about 150 million years ago and are now passing through each other. The hot gas between the galaxies visible in X-ray images represents most of the normal visible matter, and it's been slowed and heated by the collision remaining near the collision site. But gravitational lensing measurements show that most of the mass, the dark matter, passed right through without slowing down. The dark matter isn't concentrated where the visible matter is. This is strong evidence that dark matter exists as actual particles, not just a modification of gravity's behavior, because modified gravity theories would predict the gravitational effect to be centered where the visible mass is. Now, let's connect this back to something you experience every day. We've talked about GPS relying on accounting for space-time curvature to maintain accuracy. But there's another everyday technology that depends on understanding gravity as space-time curvature satellite orbits themselves. When engineers design satellite trajectories, they must account not just for Earth's mass, but for how that mass is distributed. Earth isn't a perfect sphere. It bulges slightly at the equator and has density variations from mountains, ocean trenches, variations in the thickness of Earth's crust. Each of these variations creates a slightly different space-time curvature, which affects satellite orbits over time. Without correcting for these variations, satellites would slowly drift from their intended paths. The GRACE mission, the Gravity Recovery and Climate Experiment, consisted of two satellites following each other in orbit, continuously measuring the tiny distance changes between them as they flew over regions of slightly different gravitational strength. These measurements mapped Earth's gravitational field with unprecedented precision, revealing not just mountains and trenches, but underground water reserves, ice mass changes in Greenland and Antarctica, even the redistribution of mass caused by large earthquakes. This is space-time curvature being measured in real time, affecting technology we rely on, revealing changes in our planet's mass distribution. When ice sheets melt, when aquifers are depleted, when tectonic plates shift the shape of space-time around Earth, changes ever so slightly, and sensitive instruments can detect it. Gravity, or rather the geometry of curved space-time, is not some abstract concept. It's the literal shape of reality, measurable, consequential, and dynamic. Let's talk about scales. Earth, with its mass of about 6 times 10 to the 24th kilograms, curves space-time gently. At Earth's surface, the curvature is so slight that light's path bends imperceptibly, and time dilation is measured in nanoseconds. The Sun, 333,000 times more massive, creates curvature strong enough to deflect starlight measurably, as Eddington showed. A neutron star with the Sun's mass and a sphere the size of a city curves space-time so steeply that it creates phenomena we still struggle to fully understand. And a stellar mass black hole, perhaps 10 or 20 times the Sun's mass, but compressed into a region smaller than a city, curves space-time so severely that it creates an event horizon, a boundary beyond which escape is impossible. But stellar mass black holes aren't the most extreme. At the centers of galaxies lurk supermassive black holes, millions or billions of times the Sun's mass. The one at the center of our Milky Way galaxy, Sagittarius A star, is about 4 million solar masses. The event horizon of such a black hole is enormous, a sphere that would fit comfortably within Mercury's orbit. Despite its tremendous mass, the curvature at the event horizon of a supermassive black hole is actually gentler than at the event horizon of a stellar mass black hole, because the curvature depends not just on total mass, but on density. A larger black hole has its mass spread over a larger event horizon, so the space-time curvature at the horizon is less severe. You could in principle cross the event horizon of a supermassive black hole without immediately noticing anything catastrophic. You wouldn't be instantly torn apart by tidal forces, not yet. But you'd be doomed nonetheless, falling inexorably inward, unable ever to send a signal back out. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark region created by the event horizon, surrounded by the bright ring of light from infalling matter. The black hole they imaged is at the center of the galaxy, M87, about 55 million light-years away, with a mass of about 6.5 billion suns. The image showed a dark circle surrounded by an asymmetric bright ring, exactly as general relativity predicted. Light from behind the black hole curves around it, some heading toward us, creating the ring. Light heading inward crosses the event horizon and vanishes. The shadow is the visual imprint of space-time so curved that light cannot escape. It's a photograph of geometry of the shape of the universe in an extreme condition. Think about that for a moment. We've photographed the shape of space-time. We've captured an image of curvature so severe it traps light. The equations Einstein wrote in 1915 predicting this were confirmed with a photograph in 2019. The fabric of the universe bent by mass is not metaphor, it's measurable reality. So, what have we learned about how mass curves space-time? We've learned that the curvature is real, measurable, and consequential. We've learned that it affects everything from the path of starlight during an eclipse to the orbits of satellites around Earth, to the way distant galaxies appear distorted in our telescopes. We've learned that curvature scales with mass and density from Earth's gentle dimple, to the Sun's deeper well, to neutron stars' steep slopes, to black holes' inescapable pits. And we've learned that this curvature isn't just about space. It also involves time. Clocks tick at different rates, depending on how deep they sit in a gravitational well, how severely space-time is curved around them. Which brings us to perhaps the strangest consequence of space-time curvature, one that challenges our most basic intuitions about the nature of time itself. Because if mass warps space-pulling geodesics together, steering light along curves, it also warps time, causing clocks to run at different speeds, causing the flow of moments themselves to vary, depending on where you are in the universe. And that's the territory we're about to explore. We've seen how mass warps the fabric of space, bending light, creating gravitational lenses, shaping the paths that objects follow through the cosmos. But there's another dimension to this warping one that's far more unsettling to our intuitions, far more personal in its implications. Mass doesn't just curve space, it curves time itself. Right now, the clock on your nightstand is ticking slightly faster than a clock at sea level. If you're on the second floor of your house, time flows a tiny bit quicker for you than for someone downstairs. The difference is minuscule, measured in billionths of a second over a lifetime, but it's real, measurable, inevitable. Your head is aging faster than your feet, not because of biology, but because of geometry. Because time itself flows at different rates depending on how deep you are in a gravitational well, how severely space-time is curved around you. And if that makes you wonder what time really is, whether the steady tick-tock we build our lives around is as fundamental as we've always believed, then you're beginning to touch one of the deepest mysteries Einstein's theory revealed. If you're enjoying these explorations into the nature of reality, these quiet revelations about the universe's hidden architecture, I'd be grateful if you'd like this video and subscribe to the channel. Sharing these moments of wonder helps more people discover the beauty hidden in physics. The story of time dilation begins surprisingly not with Einstein's general relativity in 1915, but with his special relativity in 1905. Special relativity revealed that time is not absolute, that moving clocks tick slower than stationary ones. If you could board a spaceship and accelerate to near the speed of light, then return to Earth, you'd find that less time had passed for you than for those who remained behind. This is the famous twin paradox. Though it's not really a paradox, once you understand that acceleration breaks the symmetry between the twins' reference frames. The traveling twin experiences time dilation because of their high velocity. They age less. Their biological clocks, their atomic clocks, their perceptions all slow down relative to the stay-at-home twin. But special relativity dealt only with motion through space. It didn't include gravity. And when Einstein extended his theory to include gravity, he discovered something equally strange. Gravity itself dilates time. The deeper you are in a gravitational field, the more severely space-time is curved, the slower your clock ticks relative to someone further out in weaker gravity. This is gravitational time dilation, distinct from but related to the velocity-based time dilation of special relativity. Einstein arrived at this conclusion through what he called the happiest thought of his life. In 1907, sitting in the potent office in Bern, he imagined a person falling freely from a roof. The person would feel weightless during the fall. They would experience no gravitational force. If they held an apple and released it, the apple wouldn't fall relative to them, because both would be accelerating downward together. Einstein realized that free fall was equivalent to floating in space far from any gravitational field. Conversely, standing still on Earth's surface was equivalent to being accelerated upward by the ground. Gravity and acceleration were two sides of the same coin, indistinguishable locally. This principle of equivalence became the foundation of general relativity. From this principle, Einstein derived a startling prediction. Imagine a light source at the bottom of a tower and a detector at the top. Light is emitted as a wave with a certain frequency. But as the light climbs upward, moving against the gravitational field, it loses energy. Since a light wave's energy is proportional to its frequency, the frequency must decrease. The light gets shifted toward lower frequencies, longer wavelengths. An observer at the top measures a lower frequency than the source emitted at the bottom. But here's the key. The source at the bottom is emitting light at a steady rate, ticking like a clock. If the detector at the top measures a lower frequency, it must conclude that the clock at the bottom is running slow. Time passes more slowly at the bottom of the tower than at the top. This seems impossible. How can time, that universal backdrop against which all events unfold, that steady march from past to future, flow at different rates in different places? But it does. And the first experimental confirmation came in 1959 in a tower at Harvard University. Robert Pound and Glenn Rebka set up an extraordinarily precise experiment using the Moosbauer effect, which allows measurement of tiny frequency shifts in gamma rays. They placed a gamma ray source of iron-57 in the basement of Harvard's Jefferson Tower and a detector at the top 22.5 meters higher. According to general relativity, the gamma rays emitted from the basement should be redshifted by about 2 parts in 10 to the 15th by the time they reach the top. That's a shift in almost incomprehensibly small effect. Yet, Pound and Rebka measured it. The frequency shift matched Einstein's prediction to within 1%. Time at the bottom of the tower ran slower than time at the top by exactly the amount general relativity predicted. Think about what this means. Over the height of a building, time's flow changes measurably. Extend this to larger scales and the effects become profound. Time at sea level runs slower than time on a mountaintop. Time on Earth runs slower than time far out in space. And near a massive object, like a neutron star or black hole, time can slow to a crawl compared to distant regions. Let's make this concrete with numbers. On Earth's surface, gravitational time dilation causes clocks to run slow by about 1 part in 10 billion compared to a clock infinitely far away, where space-time is flat. That means, for every 10 billion seconds that pass far from Earth, about 31.7 years, 1 less second passes on Earth's surface. It's a tiny effect, but it accumulates. Over a human lifetime of 80 years, a clock on Earth loses about 0.25 seconds compared to a clock in deep space. Your head being farther from Earth's center experiences slightly weaker gravity than your feet. Over a lifetime, your head ages about 90 billionths of a second more than your feet. You are not uniform in time. Now, let's scale this up. The International Space Station orbits about 400 kilometers above Earth's surface. Up there, gravity is weaker space-time, less curved, so time flows faster than on the ground. But the ISS is also moving at about 28,000 kilometers per hour, and this high velocity causes time dilation from special relativity that slows clocks down. Which effect wins? The velocity effect is stronger. Astronauts on the ISS age slightly slower than people on Earth. After 6 months in orbit, an astronaut returns about 0.007 seconds younger than if they had stayed on the ground. It's a tiny difference, but it's real. Astronauts are time travelers moving ever so slightly into everyone else's future. But these are gentle effects. To see gravitational time dilation in its full mind-bending glory, we need to venture closer to more massive objects. Let's travel in thought to a neutron star. Imagine you're in a spaceship hovering at a safe distance above a neutron star's surface, perhaps 100 kilometers up. Your companion descends in a landing craft to the surface 20 kilometers away from the star's center. The neutron star has about 1.4 times the sun's mass crammed into that tiny volume. The gravitational field at the surface is stupendously strong, about 200 billion times stronger than Earth's surface gravity. What happens to time? Your companion on the surface experiences time dilation, so severe that their clock runs about 30% slower than yours. For every 10 seconds that pass on their clock, about 14 seconds pass on yours. If they spend 1 hour on the surface, you wait 1 hour and 24 minutes in orbit. They age 1 hour. You age 84 minutes. The difference is no longer a fraction of a second. It's substantial, noticeable, life-altering if sustained over long periods. Now let's take this to the ultimate extreme, a black hole. Near a black hole's event horizon, time dilation becomes infinite. An observer far away watching someone fall toward a black hole would see the falling person's clock slow down more and more as they approach the event horizon. At the horizon itself, the person's clock would appear to stop entirely from the distant observer's perspective. They would seem frozen in time, never quite crossing the horizon, their image redshifted and dimmed, as the light they emit takes longer and longer to climb out of the deepening gravitational well. But here's the strange part. The person falling toward the black hole experiences nothing unusual at the event horizon. Their clock ticks normally from their own perspective. They cross the horizon in finite proper time, the time measured by a clock they carry with them. They don't feel time stop, but once across, they can never send a signal back out. The distant observer never sees them cross. They see the infalling person approach the horizon, asymptotically fading from view, as their light becomes infinitely redshifted. Two perspectives, two radically different experiences of time, both correct within their own reference frames. This leads to one of the strangest paradoxes in general relativity. Imagine you're falling into a black hole while your friend remains safely outside in a spaceship far away. From your friend's perspective, you never cross the event horizon. They see you slow down redshift and fade, but you never disappear. You're eternally frozen just outside the horizon. But from your perspective, you cross the horizon smoothly and continue falling inward, reaching the singularity at the black hole's center in a finite and often quite short amount of time. Both views are correct. Time is not a single universal flow. It's a local relative phenomenon, inextricably tied to the curvature of space-time. This has profound implications for how we understand the universe. Black holes don't just trap matter and light. They trap time itself, slowing it to a standstill at their boundaries. The event horizon is not just a spatial boundary. It's a temporal boundary, a place where the flow of time from an outside perspective becomes infinitely dilated. Let's bring this back to something more familiar and see how time dilation has been tested not just in towers and with atomic clocks on planes, but in one of the most elegant experiments ever conducted. In 1971, Joseph Haefel and Richard Keating placed 4 cesium atomic clocks on commercial airliners and flew them around the world, once eastward and once westward. These clocks were compared to reference clocks at the United States Naval Observatory. The flying clocks experienced 2 relativistic effects: time dilation from their velocity and gravitational time dilation from being at higher altitude where gravity is weaker. The eastward flying clocks, moving with Earth's rotation, had higher velocity relative to Earth's center than the ground clocks, so special relativity predicted they'd lose time. But they were also at altitude, so general relativity predicted they'd gain time. The westward flying clocks, moving against Earth's rotation, had lower velocity, so they had gained time from special relativity, and they'd also gain time from being at altitude. Haefel and Keating calculated the predicted effects and found that eastward clocks should lose 40 nanoseconds, while westward clocks should gain 275 nanoseconds compared to the ground clocks. When they compared the clocks after the flights, the measurements matched the predictions within experimental error. Eastward clocks lost 59 nanoseconds. Westward clocks gained 273 nanoseconds. Time dilation both from gravity and motion was confirmed on a commercial airliner. Has there ever been a moment in your life when you felt time slow down or speed up? Perhaps during an emergency when seconds stretched into what felt like minutes, or during a joyful moment that seemed to pass in an instant. Those are psychological effects, products of how your brain processes and remembers experiences. But gravitational time dilation is different. It's not perception, it's physical. Clocks literally tick at different rates. Particles decay at different rates. Biological processes unfold at different rates. Everything that depends on time, which is everything, is affected. This brings us to what might be the most famous fictional depiction of gravitational time dilation, the water planet scene in the film Interstellar. The crew lands on a planet orbiting extremely close to a supermassive black hole named Gargantua. The planet experiences such severe time dilation that 1 hour on its surface equals 7 years, back on their spaceship orbiting farther out. Is this scientifically plausible? Actually, yes. Kip Thorne, the physicist who consulted on the film, calculated that for a rapidly spinning black hole, this kind of time dilation is possible if the planet orbits close enough to the black hole without crossing the event horizon. The crew spends about 3 hours on the planet, and when they return to the ship, 23 years have passed. Their colleague who stayed behind has aged 2 decades. The math works. The physics is sound. It's an extreme case requiring an enormous black hole and a very specific orbit, but it's within the laws of general relativity. Now consider the implications for space travel. If we ever develop the technology to travel to distant stars, time dilation could be both a curse and a blessing. A spaceship accelerating to a significant fraction of light speed would experience time dilation due to velocity. Astronauts aboard would age less than people on Earth. A journey that takes decades by Earth's clocks might take only years by the astronauts' clocks. They could visit distant stars and return to find that centuries had passed on Earth. Everyone they knew would be gone. Civilizations might have risen and fallen. But from the astronauts' perspective, the journey would be survivable a human lifetime or less. Time dilation could make the stars accessible to individuals, even if not to civilizations. Gravitational time dilation adds another layer. If astronauts ventured close to a black hole or neutron star, even briefly they could experience extreme time dilation. They might age only days or weeks, while decades or centuries passed elsewhere. This could be used intentionally as a form of time travel to the future. Want to see what Earth looks like in 100 years? Spend a few weeks near the event horizon of a black hole. When you return, a century will have passed. Of course, the engineering challenges of surviving near a black hole are immense, probably insurmountable with any foreseeable technology. But the physics permits it. General relativity allows time travel to the future through gravitational time dilation. What about time travel to the past? This is where things become murky. General relativity doesn't forbid closed time-like curves paths through space-time that loop back to earlier moments. Certain solutions to Einstein's equations, like rotating black holes or traversable wormholes, theoretically permit travel backward in time. But these solutions require exotic matter with negative energy density, and it's unclear whether such matter can exist or be harnessed. Most physicists suspect that quantum effects or unknown physical laws will prevent closed time-like curves preserving causality. But we don't know for sure. Time travel to the past remains an open question. Time dilation also affects how we observe the universe. When we look at distant galaxies, we're seeing them as they were billions of years ago, because their light has taken billions of years to reach us. But there's an additional complication. The expansion of the universe stretches space-time, and this affects the flow of time as well. A supernova that takes 20 days to brighten and fade in its own reference frame appears to take longer when observed from Earth if it's in a distant galaxy. The expansion of space dilates time for those distant events. This cosmological time dilation has been measured by observing distant supernovae. It's yet another confirmation that time is not absolute, not universal, but woven into the fabric of space-time itself. So where does this leave us? We've learned that time, which feels like the most constant, reliable aspect of existence, is actually flexible. It bends, it stretches, it slows down in strong gravity and speeds up in weak gravity. Every moment you experience is local to you, tied to your position and motion through space-time. There is no universal now, no simultaneous present shared by everyone in the universe. The concept of simultaneity itself breaks down across distances and in curved space-time. This is unsettling. Our entire intuition about time, built from everyday experience, tells us that time flows uniformly, that the present moment is shared by all observers, that the past is gone and the future hasn't happened yet. But general relativity reveals that these intuitions are approximations valid only in weak gravity and at low velocities. In the universe at large, time is as variable as space, as curved and dynamic as the fabric it's part of. And just as mass curves space, creating paths and lenses, and orbital mechanics mass curves, time creating dilation and paradoxes and possibilities, we're only beginning to explore. Yet there's something even more remarkable that emerges from this understanding of curved space-time, something that connects directly to how we observe and study the universe. Because when space-time itself can vibrate, when the fabric can ripple like the surface of a pond, we gain an entirely new way to sense the cosmos, to detect events that emit no light, to hear the universe in addition to seeing it. We've explored how mass curves space-time, how that curvature bends light and dilates time, creating phenomena that challenge everything we thought we knew about the nature of reality. But if space-time is a fabric that can be curved, stretched, and warped, then perhaps it can do something else too. Perhaps it can vibrate. On September 14th, 2015, at 5:51 a.m., Eastern Daylight Time, Two detectors located 3,000 kilometers apart, one in Louisiana and one in Washington state, each felt space-time itself shudder. The shudder lasted only a fifth of a second. It stretched and compressed space by an amount smaller than the width of a proton. But in that brief moment, humanity detected something Einstein predicted 99 years earlier, but thought we'd never actually observe gravitational waves ripples in the fabric of space-time itself, carrying information about the most violent events in the universe. And the source of those ripples was a collision so energetic, so catastrophic, that it converted 3 times the mass of our sun into pure gravitational radiation in a fraction of a second, 1.3 billion light-years away. If you find yourself captivated by the idea that we can now listen to the universe that we've developed ears for space-time itself, then please consider liking this video and subscribing. These stories of scientific discovery told softly reach more people when you share them. Let's go back to 1916. Einstein had just published his general theory of relativity the previous year, and he was exploring its mathematical consequences. He discovered that his field equations, the ones describing how mass curves space-time, permitted wave solutions. Just as electromagnetic fields can oscillate and create electromagnetic waves, light waves that travel through space, space-time itself could oscillate and create gravitational waves. These waves would be distortions in the geometry of space and time, traveling at the speed of light, stretching and compressing distances as they passed. Einstein calculated that any accelerating mass would produce gravitational waves, but the amount of energy radiated would be vanishingly small for ordinary objects. Earth orbiting the sun produces gravitational waves, but the power radiated is only about 200 watts, less than 3 light bulbs spread across the entire solar system. You'd never detect such weak waves. Einstein himself doubted gravitational waves would ever be observed directly. In 1936, he even wrote a paper claiming gravitational waves didn't physically exist, though he later retracted it after realizing he'd made a mathematical error. The reason gravitational waves are so difficult to detect is that gravity is by far the weakest of the 4 fundamental forces. Electromagnetic forces are about 10 to the 36th times stronger than gravitational forces. This means that producing strong gravitational waves requires truly stupendous amounts of mass moving at extremely high speeds, and detecting those waves requires measuring distance changes far smaller than an atomic nucleus. For decades, this seemed impossible. But some physicists refused to believe it was impossible. In the 1960s, Joseph Weber at the University of Maryland built the first gravitational wave detectors. These were large aluminum cylinders about 2 meters long and 1 meter in diameter, suspended by wires and isolated from vibrations. Weber's idea was that a passing gravitational wave would cause the cylinder to ring like a bell vibrating at its resonant frequency. He placed detectors in Maryland and Illinois, hoping to see simultaneous vibrations that would indicate a gravitational wave passing through Earth. Weber claimed to have detected signals, but other physicists couldn't replicate his results. His detectors weren't sensitive enough. The noise from seismic activity, thermal vibrations, and other sources overwhelmed any genuine gravitational wave signal, but Weber's work inspired a new generation of physicists to think bigger. In the 1970s and 1980s, Rainer Weiss at MIT, Kip Thorne at Caltech, and Ronald Drever, also at Caltech, began developing a different approach: laser interferometry. Instead of waiting for a gravitational wave to make a solid object vibrate, they would measure how a gravitational wave stretched and compressed space itself by using laser beams traveling along perpendicular arms several kilometers long. The principle is elegant. Imagine you have 2 arms of equal length arranged in an L shape, each arm 4 kilometers long. You shine a laser beam down each arm. The beams reflect off mirrors at the ends and return to the corner where they started. If both arms are exactly the same length, the beams return at the same time and interfere constructively or destructively in a predictable pattern. But if a gravitational wave passes through, it stretches space along one arm while compressing it along the perpendicular arm, then reverses the process as the wave oscillates. The lengths of the arms change the laser beams travel different distances, and the interference pattern shifts. By measuring that shift, you can detect the gravitational wave. The challenge was sensitivity. Gravitational waves from even the most violent cosmic events would change the length of a 4-kilometer arm by less than 1/10,000th the width of a proton. That's a fractional change of about 1 part in 10 to the 21st. To put that in perspective, if you were trying to measure a similar fractional change in the distance to the nearest star, Alpha Centauri 4 light-years away, you'd need to detect a change smaller than the width of a human hair. The precision required was absurd. Many physicists thought it couldn't be done, but the team persisted. In 1992, the National Science Foundation approved funding for the Laser Interferometer Gravitational Wave Observatory LIGO. 2 detectors would be built, one in Hanford, Washington, and one in Livingston, Louisiana, 3,000 kilometers apart. The separation was crucial. A gravitational wave would arrive at the 2 detectors at slightly different times, a few milliseconds apart, depending on the wave's direction. This time delay would help confirm that a signal was real, and not just local noise affecting one detector. Additionally, any local disturbance, a truck driving past a small earthquake, would only affect one detector. A genuine gravitational wave would affect both. Construction began in 1994. Each detector consisted of 2 4-kilometer-long arms, housed in steel vacuum tubes. The vacuum was essential to prevent air molecules from scattering the laser light. Inside the tubes, mirrors suspended by glass fibers hung at each end. A laser beam split in 2, traveled down each arm, bounced off the mirrors, and returned to interfere at the beam splitter. The detectors were so sensitive that they could detect disturbances from ocean waves crashing on coasts thousands of kilometers away, logging trucks passing nearby, even the quantum jitter of photons in the laser beam itself. Initial LIGO began operating in 2002 and ran until 2010 without detecting any gravitational waves. This wasn't a failure. The detectors were working as designed, but they simply weren't sensitive enough yet. Physicists had predicted that to have a reasonable chance of detecting gravitational waves, LIGO would need to be about 10 times more sensitive. So, the detectors were shut down and upgraded to advanced LIGO, with better mirrors, more powerful lasers, and improved vibration isolation. Advanced LIGO began operations on September 18th, 2015. Just 4 days earlier, on September 14th, while the detectors were still in engineering mode, being calibrated and tested before the official science run began, they detected their first gravitational wave. The signal arrived at the Livingston detector, first then, 7 milliseconds later, at Hanford, consistent with a wave traveling at the speed of light from a source in the southern sky. The signal was so clear, so strong, that it was immediately obvious to the scientists reviewing the data. It looked almost too good to be true. Some researchers wondered if it might be a test signal injected into the data stream to keep the team sharp. But it wasn't. It was real. The signal, designated GW150914, matched the theoretical predictions for 2 black holes spiraling together and merging. The data revealed that 2 black holes, one about 36 solar masses and the other about 29 solar masses, had orbited each other, gradually spiraling closer as they radiated gravitational waves and lost orbital energy. In the final fraction of a second, they completed dozens of orbits, accelerating to about half the speed of light, before colliding and merging into a single black hole of about 62 solar masses. 3 solar masses, an amount of matter equivalent to 3 suns, had been converted entirely into gravitational wave energy in about 0.2 of a second. For that brief moment, the collision radiated more power than all the stars in the observable universe combined. And LIGO detected it as a tiny shiver in spacetime, a change in arm length of about 1,000th the width of a proton. The detection was announced on February 11, 2016, after months of verification, checking for instrumental errors, confirming that the signal wasn't a cosmic ray or a glitch or an earthquake. The announcement made headlines worldwide. It was the first direct detection of gravitational waves, confirming a century-old prediction by Einstein. It was also the first direct observation of black holes, merging the first evidence that binary black hole systems exist, and that they can spiral together and collide within the age of the universe. And it opened a new window on the cosmos, a way to observe events that emit little or no light. Think about what this means. For all of human history, we've studied the universe by collecting electromagnetic radiation, light in all its forms, from radio waves to gamma rays. But electromagnetic signals have limitations. They can be absorbed or scattered by dust and gas. They can't escape from inside black holes. Many of the universe's most energetic events are hidden from view. Gravitational waves, by contrast, pass through matter almost unaffected. They carry information from the hearts of black hole collisions, from the cores of collapsing stars, from the first moments after the Big Bang. They let us hear the universe in a way light never could. Since that first detection, LIGO has detected dozens more gravitational wave events. In 2017, the Virgo detector in Italy joined the network, adding a third observatory and improving the ability to pinpoint where in the sky the waves originated. Together, LIGO and Virgo have detected black hole mergers, neutron-star mergers, and even mixed events where a black hole consumes a neutron star. Each detection teaches us something new about these extreme objects, their populations, their properties, and the physics of matter under conditions we can never replicate on Earth. One of the most extraordinary detections came on August 17, 2017. LIGO and Virgo detected a gravitational wave signal consistent with two neutron stars colliding. Unlike black hole mergers, which emit only gravitational waves, because nothing can escape a black hole, neutron star mergers produce light as well. Shattered neutron star matter ejected at high speed, heated by radioactive decay and collisions, glows across the electromagnetic spectrum. Within seconds of the gravitational wave detection, alerts were sent to telescopes around the world. Within hours, astronomers had pinpointed the source, a galaxy called NGC 4993, about 130 million light-years away. They observed a kilonova, a brilliant explosion powered by the decay of heavy elements created in the collision. This was the first time a cosmic event had been observed in both gravitational waves and light, the beginning of multi-messenger astronomy, where we combine different ways of sensing the universe to get a complete picture. The neutron star collision also solved a long-standing mystery in astrophysics. Where do the heaviest elements in the universe come from? Elements lighter than iron are forged in the cores of stars through nuclear fusion. Iron itself is the endpoint of fusion, because fusing iron consumes energy rather than releasing it. Elements heavier than iron require additional neutrons and energy to form more than ordinary stellar processes provide. Supernovae produce some heavy elements, but calculations suggested they couldn't produce enough to account for the gold, platinum, uranium, and other heavy elements we observe in the universe. Neutron star mergers with their incredible densities and energies provide the missing production site. The kilonova from the 2017 event showed clear spectral signatures of heavy elements. Astronomers calculated that the collision produced several Earth masses of gold and platinum alone. Every gold ring, every platinum catalyst, every uranium atom on Earth was likely forged in a neutron star collision billions of years ago, then scattered into the interstellar medium, eventually incorporated into the cloud that formed our solar system. Let's pause and appreciate the engineering marvel that makes these detections possible. LIGO's mirrors are among the smoothest objects ever made, polished to within a few atoms of perfect flatness. They weigh 40 kilograms each and are suspended by few silica fibers thinner than a human hair, acting as pendulums to isolate them from ground vibrations. The laser light bounces back and forth in each arm about 300 times before recombining, effectively increasing the arm length to 1,200 kilometers to improve sensitivity. Active seismic isolation systems decouple the mirrors from ground motion using stacks of springs and masses along with sensors and actuators that counteract vibrations. Despite all this, the detectors are sensitive to vibrations from ocean waves crashing on both U.S. coasts, storms thousands of kilometers away, even logging operations in nearby forests. Every potential source of noise had to be understood, characterized, and either eliminated or accounted for in the data analysis. And even after all that, the signals are buried in noise. A typical gravitational wave signal changes the interference pattern by a tiny fraction much smaller than the random fluctuations from quantum noise, thermal vibrations, and countless other sources. Extracting the signal requires sophisticated data analysis, comparing the measured data to theoretical templates of what gravitational waves from different sources should look like. Researchers run simulations of black hole collisions, generate waveforms, and search the data for matches. It's a computationally intensive process requiring supercomputers to sift through the data and identify candidate events. Now, you might wonder if gravitational waves are so weak that it took billion-dollar detectors to find them. Why does it matter? What do we gain from detecting them? The answer is that gravitational waves give us access to phenomena we could never study otherwise. Black holes emit no light, but their collisions produce gravitational waves. The cores of supernovae are hidden behind layers of exploding stellar material, but gravitational waves escape unscathed. The first moments of the Big Bang are obscured by a veil of hot plasma that blocked light for 380,000 years. But gravitational waves from that era would pass through and could in principle be detected if we build sensitive enough instruments. Gravitational wave astronomy is like gaining a new sense hearing instead of sight, allowing us to perceive aspects of the universe that were previously invisible. There's also the thrill of confirming predictions. Einstein's equations predicted gravitational waves a century ago. For decades, they were theoretical curiosities, solutions to equations with no experimental evidence. Their detection vindicated Einstein's insight, showed that general relativity remains accurate, even in the most extreme conditions, and proved that space-time is as dynamic and responsive as Einstein envisioned. Every LIGO detection is a reminder that the universe operates according to mathematical laws. We can discover and understand that the fabric of reality, strange as it is, yields to patient inquiry and clever instrumentation. Looking forward, gravitational wave astronomy is still in its infancy. LIGO and Virgo are being upgraded to even higher sensitivity. Additional detectors are planned. Kagra in Japan is already operating, and more are proposed in India and Australia. A space-based detector called LISA, the Laser Interferometer Space Antenna, is planned for launch in the 2030s. LISA will have arms millions of kilometers long, far longer than Earth-based detectors, allowing it to detect lower-frequency gravitational waves from supermassive black holes merging at the centers of galaxies. These events radiate gravitational waves over months or years as the black holes spiral together, and LISA will observe them from beginning to end. There are also hopes of detecting gravitational waves from the early universe imprinted during cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. These primordial gravitational waves would be extraordinarily faint, and detecting them will require even more sensitive instruments, possibly space-based detectors or networks of pulsars acting as natural gravitational wave antennae. But if we succeed, we'll have a direct window into the universe's first moments, a time when the fundamental forces were unified and the seeds of all cosmic structure were planted. Gravitational waves have transformed from a theoretical prediction to an observational science in just a few years. What took Einstein a decade to formulate what physicists spent half a century building the instruments to detect is now a routine part of how we study the universe. And with each detection, we learn more about the most extreme environments, the most energetic events, the most massive objects. We're hearing the universe sing, and the song is strange and beautiful and full of information we're only beginning to decode. But gravitational waves, as remarkable as they are, represent just one aspect of how gravity shapes the universe. Because gravity doesn't just create waves and bend light and dilate time, it also orchestrates motion, governs orbits, binds together everything from binary stars to clusters of galaxies. It's the choreographer of the cosmic dance, setting objects spinning around each other in patterns that range from simple to staggeringly complex. We've heard space-time ring like a bell when massive objects collide. We've felt its ripples cross the cosmos at the speed of light. But most of the time, gravity's influence is quieter, more subtle, expressed not through cataclysmic collisions, but through elegant motion, through orbits, through dances that have continued for billions of years. Right now, as you rest here, Earth is spinning at about 1,600 kilometers per hour at the equator. Simultaneously, it's orbiting the Sun at 107,000 kilometers per hour. The Sun itself is orbiting the center of the Milky Way galaxy at 828,000 kilometers per hour, and the Milky Way is falling toward the Andromeda galaxy at 110 kilometers per second. You are not still. You are moving through space at staggering speeds, tracing a complex path determined by the gravitational influence of every massive object around you. Yet, you feel none of this motion. You feel only the push of your bed against your back. And the reason you feel motionless, despite hurtling through space at hundreds of thousands of kilometers per hour, is that you're following a geodesic, a natural path through curved space-time. You're in free fall, just like the astronauts orbiting overhead, just like the moon orbiting Earth, just like the planets orbiting the sun. If these intricate orbital mechanics, these gravitational ballets playing out across the universe, captivate your imagination as they do mine, please take a moment to like this video and subscribe to the channel. Your support helps these stories find others who love exploring the cosmos. Let's begin with the simplest case, two objects orbiting each other. You might think of Earth orbiting the Sun and imagine Earth tracing a circle around a stationary sun. But that's not quite right. Both objects orbit their common center of mass, called the barycenter. For Earth and the Sun is so much more massive, about 333,000 times Earth's mass, that the barycenter lies inside the Sun, only about 450 kilometers from the Sun's center. The Sun wobbles slightly as Earth orbits, but the wobble is tiny. For Jupiter, the most massive planet, the barycenter with the Sun lies just outside the Sun's surface. Jupiter's orbit causes the Sun to trace a small circle in space, completing one loop every 12 years, as Jupiter completes its orbit. Now, imagine two objects of similar mass orbiting each other. The barycenter lies between them, and both trace significant orbits around it. Pluto and its largest moon, Charon, are a beautiful example. Pluto is only about 9 times more massive than Charon, so the barycenter lies outside Pluto's surface in the space between them. Both Pluto and Charon orbit this point forever, facing each other because they're tidally locked. From Pluto's surface, Charon appears to hang motionless in the sky, neither rising nor setting, always in the same position, because Pluto's rotation period exactly matches Charon's orbital period. The same side of Pluto always faces Charon, and the same side of Charon always faces Pluto. They're locked in a gravitational embrace, bound together by the curvature of space-time. They create their mutual orbit stable for billions of years. Binary star systems offer even more dramatic examples. About half of all stars in the Milky Way exist in binary or multiple star systems, bound to one or more companion stars. Alpha Centauri, the closest star system to our Sun, is actually a triple system. Alpha Centauri A and B are similar in mass, orbiting each other every 80 years, with a separation that varies from about the distance between our Sun and Saturn to about the distance between the Sun and Pluto. Meanwhile, Proxima Centauri, A small red dwarf orbits the pair at a distance of about 13,000 astronomical units, taking about 550,000 years to complete one orbit. The dynamics are complex. Alpha Centauri, A and B perturb each other's orbits, and Proxima's distant presence creates subtle long-term changes. Yet the system is stable. It has existed for billions of years and will continue for billions more. Some binary systems are far more extreme. There are stars orbiting each other so closely that their outer atmospheres touch, transferring mass from one star to the other. These are called contact binaries or over-contact binaries. Gravity pulls them together, but their orbital motion keeps them from colliding. They're spiraling slowly closer, losing energy to tidal forces and angular momentum transfer. Eventually, they may merge into a single star. Or if one is a compact object like a white dwarf or neutron star, they may produce a supernova when enough mass is transferred to trigger runaway nuclear reactions. Then there are systems like PSRJ 0737-3039, the double pulsar. Two neutron stars, each only about 20 kilometers across, but containing more mass than the Sun, orbit each other every 2.4 hours. They're so close that they fit comfortably inside the Sun's diameter. Both are pulsars emitting beams of radio waves that sweep across Earth like cosmic lighthouses. Astronomers can measure their orbital motion with extraordinary precision by timing the pulsar signals, and they've found that the orbit is shrinking. The two neutron stars are spiraling together, losing energy by radiating gravitational waves, exactly as general relativity predicts. In about 85 million years, they'll collide, producing a gravitational wave signal similar to the ones LIGO has detected, and possibly creating a kilonova visible across the universe. But let's shift from binary systems to planetary systems, where gravity orchestrates even more intricate dances. Our solar system contains 8 planets, 5 dwarf planets, hundreds of moons, and countless asteroids and comets, all moving under the Sun's gravitational influence. The inner planets, Mercury through Mars, orbit relatively quickly. Mercury completes an orbit in 88 days. Earth takes 365 days. Mars takes 687 days. The outer planets move more slowly. Jupiter takes nearly 12 years, Saturn nearly 30 years, Uranus 84 years, Neptune 165 years. These different orbital periods create alignments and configurations that repeat in complex patterns. One of the most beautiful patterns is orbital resonance, where the orbital periods of two bodies form a simple integer ratio. Jupiter and its moons provide classic examples: Io, Europa, and Ganymede. 3 of Jupiter's largest moons are locked in a 1-2-4 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This isn't coincidence. It's gravitational choreography. The resonance arose through tidal interactions and has been maintained for millions of years. The result is that the 3 moons never align in certain configurations, which would create strong gravitational perturbations. Instead, they maintain stable orbits protected by the resonance. Neptune and Pluto are also in resonance, a 2-to-3 ratio. For every 2 orbits Neptune completes, Pluto completes 3. This resonance means that even though Pluto's orbit crosses Neptune's, bringing Pluto closer to the Sun than Neptune for part of its orbit, the two never collide. Whenever Pluto crosses Neptune's orbital path, Neptune is far away on the other side of the Sun. The resonance ensures they're never in the same place at the same time. It's a gravitational arrangement that has persisted for billions of years, a testament to the stability orbital resonances can provide. One of the most extraordinary examples of resonance is the TRAPPIST-1 system, a small red dwarf star about 40 light-years from Earth, with 7 Earth-sized planets. All 7 planets orbit closer to their star than Mercury orbits our Sun, and they're locked in a chain of resonances moving outward. The orbital periods form ratios, close to 85533323243 and 32. If you stood on one planet and watched the others pass by, you'd see them move in a complex but repeating pattern, a celestial dance choreographed by gravity. The resonance stabilizes the system, despite the planets being packed so closely together. Without it, gravitational interactions would likely destabilize the orbits, possibly ejecting planets or causing collisions. Now, let's talk about a common misconception. Why don't orbiting objects fall down? It's a question children ask, and the intuitive answer seems to be that something must be holding them up, counteracting gravity. But there's no upward force. The moon isn't being held up by anything. It's falling, constantly. The key is that it's also moving sideways fast enough that as it falls toward Earth, Earth's surface curves away beneath it. The moon keeps missing the ground. It's in perpetual free fall following the curved geodesic that its velocity and Earth's mass create. Imagine you're standing on a tall mountain with a cannon. Fire a cannonball horizontally. It travels forward while simultaneously falling downward under gravity. It lands some distance away. Fire the cannon faster. The cannonball travels farther before hitting the ground. Now, fire it at exactly the right speed, about 8 kilometers per second at Earth's surface, and something remarkable happens. The cannonball travels forward, falls toward Earth, but Earth's surface curves away beneath it at the same rate it falls. The cannonball never hits the ground. It's in orbit. This thought experiment, originally conceived by Isaac Newton and published in his Principia, illustrates that orbital motion is just projectile motion, where the projectile never lands. Astronauts on the International Space Station aren't floating because there's no gravity up there. Gravity at the ISS's altitude is about 90% as strong as on Earth's surface. They're floating because they're in free fall, falling around Earth at 28,000 kilometers per hour. The station and everything inside it, including the astronauts, fall together. There's no floor pushing up, no sensation of weight, because nothing is preventing them from following their natural geodesic. They're weightless, not because gravity is absent, but because they're freely following the path gravity dictates. This brings us to one of the most useful applications of orbital mechanics, gravitational assists, or gravity slingshots. When a spacecraft passes close to a planet, the planet's gravity bends the spacecraft's trajectory. But more than that, the spacecraft can gain or lose speed relative to the sun by stealing or donating momentum to the planet. From the planet's reference frame, the spacecraft approaches at a certain speed and leaves at the same speed, just in a different direction. But from the sun's reference frame, the spacecraft's speed can change dramatically. The Voyager missions made brilliant use of gravitational assists. Voyager 2, launched in 1977, visited Jupiter, Saturn, Uranus, and Neptune, a grand tour of the outer solar system. Without gravitational assists, the trip would have taken decades longer and required far more fuel than the spacecraft could carry. Instead, Voyager 2 used Jupiter's gravity to accelerate toward Saturn, Saturn's gravity to accelerate toward Uranus, and Uranus's gravity to accelerate toward Neptune. Each encounter increased the spacecraft's speed and changed its trajectory, sending it to the next target. The spacecraft essentially borrowed kinetic energy from the planet's orbital motion. Jupiter, Saturn, Uranus, and Neptune each slowed down infinitesimally in their orbits, losing a tiny amount of energy to Voyager 2, which gained speed. The planet's masses are so enormous that the energy loss is unmeasurable, but Voyager 2's trajectory was transformed. The Cassini mission to Saturn used multiple gravitational assists, flying past Venus twice, then Earth, then Jupiter, gaining speed at each encounter, before finally arriving at Saturn in 2004. The trajectory was carefully planned years in advance, calculating precisely when and where the spacecraft needed to pass each planet to gain the right velocity changes. It's a testament to our understanding of orbital mechanics that we can predict these encounters with such precision planning trajectories that thread a spacecraft through the solar system like a pinball through a pinball machine. Gravitational assists aren't just for gaining speed. They can also slow a spacecraft down or change its direction dramatically. The Parker Solar Probe, launched in 2018 to study the Sun's corona, uses repeated gravitational assists from Venus to gradually shrink its orbit, bringing it closer and closer to the Sun. Each Venus flyby removes some of the probe's orbital energy, allowing it to fall deeper into the Sun's gravitational well. Eventually, the probe will pass within 6 million kilometers of the Sun's surface, closer than any spacecraft has ever ventured, experiencing temperatures over 1,300 degrees Celsius, and traveling at about 700,000 kilometers per hour, the fastest human-made object ever. Now, let's consider a question you might not have thought to ask. Why are planetary orbits nearly circular? Why don't all planets follow highly elliptical paths, swooping close to the Sun, then swinging far out? The answer lies in how planets form. They coalesce from a rotating disk of gas and dust around a young star. Material in the disk orbits in roughly circular paths, all moving in the same direction in the same plane. When planets form, they inherit this circular coplanar motion. Over time, gravitational interactions between planets can change their orbits slightly, making them more or less elliptical, tilting them slightly relative to each other. But the overall structure, circular orbits in a flat disk, reflects the initial conditions of the protoplanetary disk. Planets in other star systems show more variety. Some exoplanets orbit their stars in highly elliptical orbits, swooping from near to far. Others orbit in tilted orbits inclined at steep angles relative to their star's equator, or even in retrograde orbits moving opposite to the star's rotation. These oddities likely result from gravitational interactions between planets, or between a planet and the remnant disk of material, or even close encounters with passing stars. In some cases, a massive planet may have migrated inward from the outer system, scattering other planets into eccentric or inclined orbits. Our solar system's relatively circular coplanar orbits may be unusual, a sign of a calm history, without major gravitational upheavals. There's also the three-body problem, one of the oldest unsolved problems in physics. Predicting the motion of two bodies orbiting each other under gravity is straightforward. We have exact mathematical solutions, but add a third body and the problem becomes unsolvable in general. There's no formula that predicts the positions of three mutually interacting bodies at all future times. The system can behave chaotically with tiny changes in initial conditions, leading to vastly different outcomes. Some configurations are stable, others are not. The Sun, Earth, and Moon form a three-body system, but it's stable because the Moon is much closer to Earth than to the Sun. So we can approximate it as Earth and Moon orbiting each other, with the Sun perturbing them slightly. But in systems where all three bodies have comparable masses and separations, the dynamics can be wildly unpredictable. Interestingly, certain special solutions to the three-body problem do exist. The Lagrange points are 5 positions in space where a small object can maintain a stable position relative to 2 larger orbiting objects. For the Earth-Sun system, there are 5 Lagrange points. The L1 point between Earth and the Sun is where the gravitational pulls of Earth and Sun balance the centrifugal force of orbiting, allowing a spacecraft to hover there with minimal fuel. The James Webb Space Telescope orbits the L2 point on the far side of Earth from the Sun, where it remains in Earth's shadow, shielded from the Sun's heat and light, ideal for infrared observations. The L4 and L5 points located 60 degrees ahead and behind Earth in its orbit are stable. Objects placed there tend to stay there. Jupiter has clusters of asteroids called Trojans trapped at its L4 and L5 points. They orbit the Sun in Jupiter's orbit, leading and trailing the planet by 60 degrees, held there by the gravitational interplay between Jupiter and the Sun. Can you imagine the complexity of motion in a galaxy containing hundreds of billions of stars, each influencing every other with its gravity? The Milky Way's stars don't orbit in simple ellipses. They follow complex paths rising and falling relative to the galactic plane, speeding up and slowing down as they pass through denser regions where gravity is stronger. Our Sun takes about 225 million years to orbit the galactic center, a period called a galactic year. In the Sun's 4.6 billion year lifetime, it has completed about 20 orbits. During those orbits, it has passed through the galaxy's spiral arms multiple times, regions where star density and gravitational influence are higher. Each passage may have perturbed the orbits of comets in the solar system's outer reaches, sending some plunging toward the inner solar system, possibly triggering impact events on Earth. Galaxies themselves move under gravity's influence. The Milky Way and Andromeda are falling toward each other at about 110 kilometers per second. In about 4.5 billion years, they'll collide. I say collide, but galaxies are mostly empty space. Stars are so far apart that during a galactic collision, very few stars actually hit each other. Instead, the galaxies pass through each other, their gravitational fields interacting, distorting their shapes, triggering bursts of star formation as gas clouds collide and compress. Over hundreds of millions of years, the two galaxies will merge, eventually settling into a single elliptical galaxy that astronomers have nicknamed Milkomeda. Our Sun will likely survive the merger unscathed, though its orbit around the new galactic center will be different. Gravity orchestrates all of this, from the Moon's orbit around Earth to binary stars spiraling together, to planets locked in resonance, to galaxies colliding and merging. Every motion follows the curvature of space-time, every trajectory determined by mass and velocity and the geometry they create. There's no conductor, no grand plan, just objects following geodesics, shaping space-time, and being shaped by it, in turn creating a cosmic dance that has played out for billions of years and will continue for billions more. But there's something curious we haven't addressed yet. When we calculate how fast stars should orbit in galaxies based on the visible matter, the stars and gas, we can see the numbers don't match observations. Stars move faster than they should, as if there's more mass present than we can detect. And this discrepancy isn't small. It suggests that most of the mass in galaxies, most of the gravity shaping their structure and motion, comes from something we cannot see. We've traced the elegant motions of planets and stars, watched binary systems dance and galaxies spiral. We've calculated orbits using the masses. We can see the stars and gas that shine across the electromagnetic spectrum. But when astronomers measured how fast stars actually move in galaxies, they discovered something deeply unsettling. The numbers didn't match. Stars were moving too fast. Galaxies were spinning so rapidly that, given their visible mass, they should have torn themselves apart billions of years ago, flinging stars into intergalactic space like water droplets flying off a spinning wheel. They didn't. The galaxies held together, which means there's more mass present, more gravity at work than we can see. About 5 times more. 85% of the matter in the universe doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. It reveals itself only through gravity, through the way it curves space-time, through the way it holds galaxies together and shapes the large-scale structure of the cosmos. We call it dark matter, not because it's literally dark, but because it's invisible to every telescope we've built. And without it, galaxies wouldn't exist, planets wouldn't exist, you wouldn't exist. If the idea that most of the universe's mass is hidden from view intrigues you, if you want to explore more mysteries that challenge our understanding of reality, please like this video and subscribe. These journeys into the unknown reach further when you share them. The story of dark matter begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a large collection of over 1,000 galaxies about 320 million light-years away. He measured the velocities of galaxies in the cluster by observing their Doppler shifts, the change in wavelength of their light due to motion. Some galaxies were moving toward us, blue-shifted. Others were moving away redshifted. By analyzing the distribution of velocities, Zwicky could estimate how much mass the cluster contained. He used a principle called the virial theorem, which relates the kinetic energy of objects in a gravitationally bound system to the gravitational potential energy holding them together. The faster the galaxies moved, the more mass the cluster needed to keep them bound. When Zwicky did the calculation, he found something shocking. The galaxies were moving so fast that the cluster needed about 400 times more mass than the visible galaxies contained to prevent them from flying apart. There was too much kinetic energy, too much motion for the visible matter to explain. Zwicky proposed that most of the cluster's mass was dunkel Materie, dark matter, invisible material that exerted gravitational force but emitted no light. His contemporaries largely dismissed the idea. Perhaps he had made an error. Perhaps the cluster wasn't gravitationally bound and would eventually disperse. Perhaps the visible galaxies contained more mass than estimated. The concept of dark matter was too radical, too strange, and it languished for decades. Then, in the 1970s, an American astronomer named Vera Rubin revived the dark matter hypothesis with even more compelling evidence. Rubin studied the rotation curves of spiral galaxies graphs, showing how fast stars and gas orbit at different distances from the galactic center. According to Newton's and Einstein's laws, once you're far enough from the center, that most of the galaxy's mass is interior to your orbit. Your orbital velocity should decrease with distance just as outer planets in our solar system orbit more slowly than inner planets. The sun holds the planets in their orbits, and planets farther out feel weaker gravity and move more slowly. But when Rubin measured the rotation curves of galaxies, she found that stars far from the galactic center were moving just as fast, or sometimes even faster than stars closer in. The rotation curves were flat, not declining. This was impossible if the galaxy's mass was concentrated in the visible stars and gas. It implied that mass extended far beyond the visible disk, forming a halo of invisible matter that kept the outer stars moving faster than they otherwise would. Rubin's observations were meticulous, conducted over years with increasingly precise instruments. She studied dozens of galaxies. The pattern held. Flat rotation curves were the norm, not the exception. The galaxies were embedded in halos of dark matter, extending far beyond their visible edges, containing 5 to 10 times more mass than all the stars and gas combined. Without this dark matter, the galaxies would fly apart. Stars on the outer edges would escape into intergalactic space. The galaxies couldn't exist in their current form. Think about what this means. When you look at a photograph of a spiral galaxy, like the Milky Way or Andromeda, the beautiful glowing disk of stars and the bright central bulge you're seeing less than 20% of the galaxy's mass. The rest is dark matter, forming an enormous spherical halo that envelops the visible galaxy. The stars you see are like fireflies, illuminating the outline of an invisible giant. The dark matter halo is the dominant mass, the gravitational scaffolding upon which the visible galaxy is built. So, what is dark matter? That's the question that has occupied physicists for nearly a century. It's not ordinary matter. Atoms made of protons, neutrons, and electrons just too dim to see. We know this because ordinary matter interacts with light and with itself in ways that would produce observable effects. Clouds of cold hydrogen in space absorb specific wavelengths of light. Hot gas emits X-rays. Stars form when gas clouds collapse under gravity. If dark matter were made of ordinary atoms, we'd see these signatures. We don't. Dark matter must be something else, some form of matter that doesn't interact with electromagnetism, only with gravity. Several candidates have been proposed. The leading hypothesis is that dark matter consists of WIMPs, weakly interacting massive particles. These would be subatomic particles perhaps 10 to 100 times the mass of a proton that interact only through gravity, and possibly the weak nuclear force which governs certain types of radioactive decay. WIMPs would pass through ordinary matter almost entirely unaffected. Trillions of them might be streaming through your body right now, passing through Earth, through the Sun, without interacting with a single atom. Yet, collectively, their mass would dominate the gravitational landscape of the universe. Physicists have built detectors deep underground, shielded from cosmic rays and other interference, trying to catch a WIMP interacting with an atomic nucleus. The detectors contain tons of ultra-pure materials cooled to near absolute zero, monitored by sensitive instruments. The idea is that very rarely a WIMP will collide with a nucleus, causing it to recoil, depositing a tiny amount of energy that the detectors can measure. Far after decades of searching, no confirmed WIMP detection has been made. Either WIMPs are even more weakly interacting than expected, or they're not the right explanation. Another candidate is the axion, a hypothetical particle much lighter than a WIMP, perhaps 1,000,000 times lighter than an electron. Axions were originally proposed to solve a problem in particle physics unrelated to dark matter, but they happen to have properties that make them good dark matter candidates. They would interact even more weakly than WIMPs, making them extraordinarily difficult to detect. Experiments are underway to search for axions by looking for their subtle effects on electromagnetic fields, but no detection has been confirmed yet. A third possibility is primordial black holes that formed in the early universe, not from collapsing stars, but from dense regions of matter collapsing under their own gravity shortly after the Big Bang. These black holes could have a wide range of masses from tiny smaller than an atom to thousands of solar masses. They would be invisible, emitting no light detectable only through their gravitational effects. However, various observations have constrained how much dark matter could be in the form of primordial black holes. Gravitational lensing surveys, studies of how often stars and nearby galaxies brighten when a compact object passes in front of them, suggest that primordial black holes can account for more than a small fraction of dark matter. Most dark matter must be something else. Some physicists have proposed modifying the laws of gravity instead of invoking dark matter. Perhaps gravity doesn't behave exactly as Einstein's general relativity predicts on galactic scales. Perhaps there's an additional term in the equations that causes gravity to be stronger at large distances or in weak fields. The most developed version of this idea is called modified Newtonian dynamics, or MOND. MOND adjusts Newton's second law, proposing that at very low accelerations, like those experienced by stars in the outer regions of galaxies, gravity behaves differently, causing objects to move faster than standard Newtonian gravity predicts. MOND can fit some rotation curve data quite well without invoking dark matter, but it struggles to explain other observations. It can account for the gravitational lensing we observe around galaxy clusters, where light from background galaxies is bent by the cluster's mass. The amount of lensing requires more mass than the visible matter provides, and MOND alone doesn't produce enough additional gravitational effect. MOND also can't easily explain the cosmic microwave background, the afterglow of the Big Bang, whose patterns encode information about the density and composition of matter in the early universe. Those patterns match predictions based on dark matter, not modified gravity. The strongest evidence for dark matter as actual particles comes from a cosmic collision called the Bullet Cluster. In 2006, astronomers analyzed this system, where two galaxy clusters collided about 150 million years ago and are now passing through each other. When clusters collide, the galaxies themselves, which are mostly empty space, pass through with little interaction. But the hot gas between the galaxies, which makes up most of the ordinary matter, collides, slows down, and piles up near the collision site. This gas emits X-rays, so we can see exactly where it is. Now, if dark matter exists as particles that interact only gravitationally, it should behave like the galaxies passing through the collision, largely unaffected, continuing onward with minimal slowdown. If, on the other hand, there's no dark matter, and the gravity is just stronger than we think, then the gravitational potential should be centered, where the ordinary matter, the hot gas, is located. So, whereas the mass gravitational lensing measurements show that the mass is not centered on the hot gas. It's centered on the galaxies which have passed through and are now separated from the gas. The dark matter unaffected by the collision traveled with the galaxies and is now offset from the visible ordinary matter. This is strong evidence that dark matter is real, that it's made of particles, and that it interacts very weakly with ordinary matter. Dark matter isn't just a curiosity for astrophysicists. It's fundamental to the structure of the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny density variations about 1 part in 100,000. Gravity amplified these variations. Denser regions attracted more matter, becoming denser still, eventually forming the first stars and galaxies. But ordinary matter couldn't start this process efficiently. In the early universe, ordinary matter was hot and ionized, interacting strongly with radiation. Photons constantly scattered off electrons, preventing matter from clumping together, until the universe cooled enough for atoms to form about 380,000 years after the Big Bang. Dark matter, however, didn't interact with radiation. It could start clumping immediately, forming gravitational wells that ordinary matter later fell into. Dark matter provided the scaffolding, the initial structure upon which galaxies formed. Computer simulations of cosmic structure formation show that without dark matter, galaxies as we know them wouldn't exist. Ordinary matter alone couldn't have clumped into galaxies quickly enough. The universe would look vastly different perhaps, just a diffuse sea of gas with no stars, no planets, no life. The distribution of dark matter in the universe follows a pattern called the cosmic web. Gravity pulled dark matter into vast filaments and sheets with enormous voids in between. At the intersections of filaments where matter was densest, galaxy clusters formed. Galaxies formed along the filaments. Voids, regions with very little matter, expanded as surrounding regions contracted. Maps of galaxy positions reveal this structure: clusters, filaments, and voids stretching across hundreds of millions of light years. This is the architecture of the cosmos, shaped by gravity acting on dark matter over billions of years. Our own Milky Way galaxy sits within a dark matter halo that extends perhaps 600,000 light years from the galactic center far beyond the visible disk, which is only about 100,000 light years across. This halo contains about 1 trillion solar masses of dark matter, compared to about 200 billion solar masses of ordinary matter in stars, gas, and dust. The dark matter dominates. Its gravity holds the galaxy together, prevents the outer stars from escaping, and influences the orbits of everything within the galaxy, including our solar system. Interestingly, dark matter's distribution is smooth on small scales. There don't appear to be clumps of dark matter within the solar system, or even within individual star systems. Dark matter interacts so weakly that it doesn't collapse into compact objects. It forms diffuse halos. So, while dark matter fills the space around you, its density is incredibly low. At any given moment, about 10 to the 20th, dark matter particles might be passing through your body, but they leave no trace, interacting with nothing detectable, only through the cumulative gravitational effect of vast quantities distributed across galactic scales. Does it bother you, lying here knowing that most of the universe is invisible, that the atoms making up your body, the air you breathe, the stars in the sky, the planets, all of it, accounts for less than 15% of the universe's matter? The rest is dark matter. Unknown particles following unknown physics shaping the cosmos in ways we're only beginning to understand. We've built our entire understanding of the universe, all of astronomy and astrophysics, on observing light. Yet light reveals only a fraction of what exists. The universe is far stranger, far more hidden than our senses can perceive. But here's what we do know: dark matter is real. Its gravitational influence is undeniable. It holds galaxies together, bends light, shapes the cosmic web. It's woven into the fabric of space-time, as surely as ordinary matter, curving geodesics, guiding the motion of stars and galaxies. And while we don't yet know what it is, every telescope we build, every detector we deploy, every simulation we run brings us closer to understanding it. One day we'll detect dark matter particles, directly measure their properties, understand their origins. And when we do, it will be one of the greatest discoveries in the history of science, revealing a hidden component of reality that's been shaping the universe since its birth. Yet, dark matter is only part of the story. Because gravity didn't just shape the structures we see today. It built them from scratch, starting from nearly uniform conditions, shortly after the Big Bang, sculpting the cosmic web, igniting the first stars, assembling galaxies, and continuing to drive the universe's evolution across billions of years. We have discovered that dark matter provides the gravitational scaffolding for galaxies, the invisible framework upon which visible matter accumulates. But this raises a deeper question. Where did that framework come from? How did gravity transform the nearly uniform, hot, dense soup of matter that filled the early universe into the intricate cosmic web of galaxies, clusters, filaments, and voids? We observe today, 13.8 billion years ago, the universe began in a state so hot and dense that matter as we know it couldn't exist. No atoms, no molecules, not even protons or neutrons. Just a seething ocean of fundamental particles and energy. Yet somehow, from that formless beginning, gravity sculpted everything: the first atoms, the first stars, the first galaxies, eventually planets and life itself. Gravity is the architect of cosmic structure, working patiently over billions of years, amplifying tiny imperfections into galaxies, transforming chaos into the organized universe we inhabit. And the story of how this happened is one of the most remarkable narratives in all of science. If you're captivated by the idea that the universe has a history, that structure emerged from simplicity through laws, we can understand. Please take a moment to like this video and subscribe to the channel. These cosmic stories reach more minds when you help share them. Let's start at the beginning, or as close to it as we can reliably understand. In the first fraction of a second after the Big Bang, perhaps at 10 to the negative 35 seconds, the universe underwent a period called cosmic inflation. Space expanded exponentially, doubling in size every tiny fraction of a second, driven by a field of energy that permeated all of space. This inflation smoothed out large-scale irregularities, stretching the universe until it was almost perfectly uniform. Almost, but not quite. Quantum fluctuations, tiny random variations in energy density at subatomic scales, were stretched by inflation from microscopic to cosmic scales. These fluctuations became the seeds of all future structure. Regions that were slightly denser than average would eventually attract more matter, through gravity growing into galaxies and clusters. Regions that were slightly less dense would become voids. When inflation ended, the universe was still extraordinarily hot and dense, filled with a plasma of particles, quarks, electrons, photons, neutrinos, and dark matter particles. As the universe expanded, it cooled. Within the first few microseconds, quarks combined to form protons and neutrons. Within the first few minutes, nuclear fusion in the hot, dense plasma created the first atomic nuclei, mostly hydrogen, about 25% helium by mass, and trace amounts of lithium and beryllium. This is called Big Bang nucleosynthesis, and it's one of the great confirmations of the Big Bang theory. The observed abundances of these light elements in the universe match the predictions of Big Bang nucleosynthesis almost perfectly. But the universe was still too hot for atoms to form. Electrons remained free, not bound to nuclei. Photons constantly scattered off the free electrons, making the universe opaque, a glowing fog, where light couldn't travel far before interacting with matter. This continued for about 380,000 years. Then the universe cooled enough to about 3,000 Kelvin for electrons to combine with nuclei, forming the first neutral atoms, mostly hydrogen and helium. This moment is called recombination, though it's a bit of a misnomer, since the electrons and nuclei were combining for the first time, not recombining. With electrons bound into atoms, photons could suddenly travel freely. The universe became transparent. The light from this moment stretched by the universe's expansion over 13.8 billion years is what we observe today as the cosmic microwave background radiation, a faint glow of microwave light coming from every direction in the sky. The cosmic microwave background is one of the most important discoveries in cosmology. Detected accidentally in 1965 by Arno Penzias and Robert Wilson, who were troubleshooting a sensitive radio antenna and couldn't eliminate a persistent background noise, it provides a snapshot of the universe when it was only 380,000 years old. Detailed measurements by satellites like COBE-W MAP and Planck have mapped the temperature variations in this radiation across the entire sky with extraordinary precision. The variations are tiny, about 1 part in 100,000, but they reveal the density fluctuations present in the early universe, the seeds from which galaxies grew. Denser regions appear slightly warmer. Less dense regions appear slightly cooler. The pattern of these fluctuations matches predictions based on cosmic inflation and dark matter, providing strong evidence for both. After recombination, the universe entered what's called the Dark Ages, a period lasting several hundred million years when no stars yet existed. The universe was filled with neutral hydrogen and helium gas, dark matter, and the faint afterglow of the Big Bang, cooling as the universe expanded. During this time, gravity was at work. Dark matter clumped first, forming gravitational wells. Ordinary matter, now free from the constant pressure of radiation, scattering off electrons, began falling into these wells, accumulating in the densest regions. Over millions of years, the gas collected into clouds, and within these clouds, the densest pockets began collapsing under their own gravity. Eventually, about 100 to 200 million years after the Big Bang, the first clouds collapsed enough that their centers became hot and dense enough to ignite nuclear fusion. The first stars were born. These stars were different from stars today. They formed from gas that contained only hydrogen and helium, no heavier elements, because no stars had yet lived and died to produce them. Without heavy elements, the gas couldn't cool efficiently, so the collapsing clouds had to be very massive before they could fragment into individual stars. The first stars, called Population 3 stars, were likely tens or even hundreds of times more massive than the Sun. They burned hot and bright, with surface temperatures over 100,000 Kelvin, emitting intense ultraviolet radiation that began ionizing the surrounding hydrogen gas, creating bubbles of ionized gas that grew and merged. This is called the epoch of reionization, when the universe transitioned from neutral to ionized, clearing the fog and allowing light to travel freely once again. These first stars lived fast and died young. Massive stars burned their nuclear fuel, quickly exhausting their hydrogen in only a few million years compared to the Sun's 10 billion year lifetime. When they exhausted their fuel, they exploded as supernovae, the first supernovae in the universe, seeding the surrounding gas with heavy elements, carbon, oxygen, silicon, iron, and others. These elements mixed into the gas clouds from which the next generation of stars formed, enabling more complex chemistry and smaller stars. The universe began, a cycle stars form, live die, enrich the gas, new stars form from the enriched gas, and the cycle continues each generation, building on the previous one. Within the first billion years, the first galaxies assembled. These early galaxies were small, perhaps 1 million to 1 billion solar masses, much smaller than the Milky Way's current 200 billion solar masses. But they were actively forming stars glowing brightly despite their small size. Gravity pulled these small galaxies together into larger structures. Galaxies merged, combining their stars and gas, growing larger with each merger. This hierarchical assembly, small structures merging into larger ones, is a fundamental prediction of the dark matter model of structure formation, and observations confirm it. When we look at distant galaxies, seeing them as they were billions of years ago, we see smaller, more numerous galaxies than we do nearby. Over time, these galaxies collide and merge, building up the massive galaxies we observe in the local universe today. One of the most iconic images in astronomy is the Hubble Deep Field, a photograph taken by the Hubble Space Telescope in 1995. Astronomers pointed the telescope at a tiny patch of sky, an area only about 1/24th the size of the full moon, seemingly empty to the naked eye. They exposed the camera for 10 days, collecting every photon they could from that tiny region. The resulting image contained about 3,000 galaxies, ranging from nearby to some of the most distant galaxies ever observed, appearing as they were over 12 billion years ago, less than 2 billion years after the Big Bang. The image was a revelation. Everywhere we look, the universe is filled with galaxies. And many of those galaxies are young, small, irregular, often colliding and merging. The universe was a more violent, chaotic place in its youth. Later in 2004, the Hubble Ultra Deep Field went even deeper, revealing about 10,000 galaxies in an even smaller patch of sky. In 2012, the Extreme Deep Field pushed the boundaries further, revealing galaxies as they appeared only 500 million years after the Big Bang. And with the launch of the James Webb Space Telescope in 2021, we're now observing the first galaxies forming, seeing the universe when it was less than 400 million years old, a time when the universe was only 3% of its current age. These observations are testing our models of galaxy formation, revealing how quickly structures assembled, how massive the first black holes were, and how the earliest galaxies enriched the universe with heavy elements. Gravity's role in all of this cannot be overstated. Every structure from the smallest star to the largest galaxy cluster formed because gravity amplified initial density fluctuations. Dense regions attracted more matter, becoming denser, still eventually collapsing into bound objects. Less dense regions lost matter to their surroundings, becoming voids. Over billions of years, this process created the cosmic web, a vast network of filaments and sheets of galaxies surrounding enormous voids. Simulations of cosmic structure formation, which model billions of dark matter particles interacting only through gravity, reproduce this structure remarkably well. The Millennium simulation, run in 2005, followed the evolution of over 10 billion dark matter particles in a cubic region about 2 billion light-years on a side. The simulation began with initial conditions set by the observed fluctuations in the cosmic microwave background, and evolved forward using only gravity. The result was a cosmic web that looks strikingly similar to what we observe when we map galaxy positions in the real universe. Filaments, clusters, voids all emerging naturally from gravity acting on dark matter. The illustrious simulation completed in 2014 went further, including not just dark matter, but also ordinary matter, gas that cools, forms, stars feeds black holes, and is heated and expelled by supernovae and black hole jets. This simulation followed the formation and evolution of thousands of galaxies, showing how they grow through gas accretion and mergers, how supermassive black holes at their centers influence their host galaxies, and how galaxies evolve from small star-forming irregular systems into large red elliptical galaxies dominated by old stars. The agreement between simulations and observations is impressive, though not perfect. There are still puzzles, still discrepancies suggesting that our understanding of star formation, black hole growth, and feedback processes isn't complete. But the fact that we can simulate the formation of realistic galaxies using known physics is a triumph of modern astrophysics. Now, let's focus on one specific example of gravitational collapse, the formation of a star. Imagine a cloud of gas, perhaps a few light-years across, containing a few thousand solar masses of hydrogen and helium floating in space within a galaxy. This cloud is cold only about 10 to 20 Kelvin, and it's supported against collapse by internal pressure and turbulent motions. But parts of the cloud, the densest regions, are on the edge of gravitational instability. If a shock wave from a nearby supernova passes through, or if the cloud collides with another cloud, it can be compressed, pushing parts of it over the threshold where gravity wins. The densest regions begin to collapse. As a region collapses, it heats up, because gravitational potential energy converts to kinetic energy and then to thermal energy through collisions. The cloud fragments into smaller clumps, each collapsing independently. Within each clump, the center becomes hotter and denser. Eventually, the temperature at the core reaches about 10 million Kelvin, hot enough for hydrogen nuclei to overcome their mutual electrostatic repulsion and fuse into helium. Nuclear fusion begins. The energy released by fusion creates outward pressure that balances the inward pull of gravity. The collapse stops. A star is born. The surrounding gas and dust still collapsing inward may form a disk around the young star. Within that disk, planets can form solid bodies, coalescing from dust and ice, growing through collisions, eventually sweeping up most of the material in their orbital paths. This is how our solar system formed 4.6 billion years ago, and likely how most planetary systems form. The entire process from initial cloud collapse to star formation takes about 10 to 50 million years for a star like the Sun. More massive stars form faster, perhaps in only 1 million years. Less massive stars take longer. But in every case, gravity is the driving force pulling matter together, converting gravitational potential energy into heat, eventually triggering fusion. Without gravity, stars couldn't form. Without stars, heavy elements couldn't be created. Without heavy elements, rocky planets and life couldn't exist. Gravity acting over cosmic timescales is the ultimate creative force in the universe. Let's also consider the role of dark matter more carefully in this process. Dark matter doesn't interact with ordinary matter, except through gravity, so it doesn't cool and collapse into compact objects like stars. Instead, it forms diffuse halos. When ordinary matter falls into a dark matter halo, it can cool by radiating energy as light, allowing it to collapse further and form stars. Dark matter unable to cool remains in a large halo. So, a galaxy like the Milky Way has two components: a visible disk of stars, gas and dust, about 100,000 light-years across, and a dark matter halo extending perhaps 600,000 light-years, maybe more. The visible galaxy sits at the center of the dark matter halo, like a pearl at the center of an enormous invisible oyster. The dark matter halo formed first collapsing under its own gravity until it reached a stable configuration, where the velocities of dark matter particles balance the gravitational pull, trying to make them fall inward. This is called virialization, and it results in a halo where the density decreases with distance from the center. Ordinary matter falling into the halo later collided with itself, radiated energy, and settled into a disk, where it could cool further and form stars. This is why galaxies have disks of stars, but dark matter doesn't form disks. Dark matter can't lose energy efficiently, so it retains its extended diffuse distribution. One might ask, why did the universe start out so uniform if tiny fluctuations were so important? The answer is that the uniformity and the fluctuations both came from cosmic inflation. Inflation stretched space so much that any large-scale irregularities were smoothed out, making the universe nearly uniform on large scales. But quantum fluctuations, random variations at the smallest scales, were also stretched, becoming macroscopic density variations. These variations were tiny, 1 part in 100,000, but they were present everywhere, on all scales. Inflation created both the uniformity and the seeds of structure. Without inflation, we'd struggle to explain why the universe is so uniform in some ways, yet structured in others. As you lie here, consider the journey that every atom in your body has taken. Hydrogen nuclei formed in the first few minutes after the Big Bang. Heavier elements were forged in stars over billions of years, released into space by supernovae, mixed into new clouds of gas, incorporated into new stars and planets. The calcium in your bones, the iron in your blood, the oxygen you breathe, All of it was created in stellar furnaces and scattered by stellar explosions, then gathered by gravity into the cloud that became our solar system, eventually ending up in you. You are made of star stuff, as Carl Sagan famously said. But more than that, you're made of stuff shaped by gravity, organized by gravity, brought together by gravity, acting over cosmic time scales and distances. Gravity didn't just build galaxies, it built the conditions for life. Without gravity pulling matter together, there would be no stars, no fusion, no heavy elements, no planets, no chemistry, no biology. The universe would be a cold, diffuse gas of hydrogen and helium, dark and sterile. Gravity. The weakest of the four fundamental forces acting over the longest time scales and the largest distances is the sculptor of complexity, the enabler of structure, the architect of a universe where stars can shine, planets can form, and life can emerge. Yet gravity's work isn't confined to individual galaxies or even clusters. On the largest scales, gravity shapes the motion of structures across hundreds of millions of light years, creating flows and attractions that pull entire galaxy clusters through space, drawing them toward concentrations of mass so vast that they rival the expansion of the universe itself. We've watched gravity build galaxies from primordial gas, sculpt the cosmic web over billions of years, and organize matter into the structures we observe throughout the universe. But there's something peculiar about the motion of galaxies that suggests gravity's influence extends even further than we've discussed. Our galaxy, the Milky Way, isn't simply drifting away from other galaxies due to cosmic expansion. It's being pulled, actively drawn towards something massive, something so gravitationally dominant that it's pulling thousands of galaxies across hundreds of millions of light years. Right now, as you rest here, you're moving toward a point in space at about 600 kilometers per second. Not because Earth is orbiting the Sun, not because the Sun is orbiting the galactic center, but because the entire Milky Way galaxy, along with Andromeda and thousands of neighboring galaxies, is falling toward an enormous concentration of mass called the Great Attractor. Meanwhile, something behind us, a vast, underdense region called the Dipole Repeller, is pushing us from the other direction like a cosmic hand at our back. We're caught in a gravitational river, flowing through space on currents shaped by the largest mass distributions in the universe. And this motion reveals that gravity's reach is truly cosmic, organizing not just galaxies, but entire clusters and superclusters across distances that challenge comprehension. If this idea fascinates you, if you want to continue exploring the forces shaping our cosmic neighborhood, please take a moment to like this video and subscribe. Your support helps these journeys through space and time reach others who share your curiosity. The story of the Great Attractor begins in the 1970s with observations of something called the cosmic microwave background's dipole anisotropy. When astronomers measured the cosmic microwave background radiation from different directions, they found it wasn't perfectly uniform. In one direction, the radiation appeared slightly blue-shifted, slightly hotter. In the opposite direction, it appeared slightly red-shifted, slightly cooler. The difference was about 1 part in 1,000 far larger than the tiny fluctuations from density variations. This pattern indicated motion. If you're moving toward a source of light, the light appears blue-shifted. If you're moving away, it appears red-shifted. The dipole pattern in the cosmic microwave background revealed that our entire local group of galaxies is moving at about 600 kilometers per second relative to the average rest frame of the universe, but moving toward what, at first, astronomers thought our motion could be explained by the gravitational pull of nearby galaxy clusters. The Virgo cluster, a large cluster containing about 1,500 galaxies located about 54 million light-years away, seemed like a plausible cause. The Milky Way is part of the local group, a small cluster containing about 80 galaxies, including Andromeda. The local group is falling toward the Virgo cluster, and we're part of a larger structure called the Virgo supercluster. So perhaps our motion was just infall toward Virgo. But the numbers didn't add up. The Virgo cluster's mass alone couldn't account for a velocity of 600 kilometers per second. Something more massive, something farther away, had to be pulling us. In 1986, a team of astronomers led by Donald Lynden Bell and others analyzed the peculiar velocities of galaxies, the deviations from pure Hubble expansion, and found evidence for a large mass concentration in the direction of the constellations Hydra and Centaurus, about 250 million light-years away. They named it the Great Attractor. The mass was estimated at tens of thousands of times the mass of the Milky Way, concentrated in a relatively small region of space. But here's the problem. When astronomers looked in that direction with telescopes, they didn't see anything particularly special. There were galaxies, certainly, but no obvious enormous cluster that could account for the inferred mass. Part of the challenge is that the Great Attractor lies in the zone of avoidance, a region of sky behind the plane of the Milky Way, where dust and stars in our own galaxy obscure our view of distant structures. Infrared and radio observations, which can penetrate dust better than visible light, revealed a large cluster called the Norma cluster in that region, but it still didn't seem massive enough. Over the following decades, astronomers mapped the distribution of galaxies, more extensively measuring distances and velocities for thousands of galaxies. They discovered that the Great Attractor itself is part of an even larger structure, the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is a colossal collection of about 100,000 galaxies spanning about 520 million light-years. The Milky Way sits near the edge of Laniakea. At Laniakea's heart lies not just one mass concentration, but several, including the Norma cluster, the Centaurus supercluster, and most significantly, the Shapley supercluster. The Shapley supercluster, located about 650 million light-years away in the direction of the constellation Centaurus, is one of the most massive structures in the nearby universe. It contains over 8,000 galaxies organized into dozens of clusters, with a total mass estimated at about 10 to the 16th solar masses, 10 million billion times the mass of the Sun. This is the true gravitational giant in our cosmic neighborhood. It's not the Great Attractor itself, but it's part of the broader mass distribution pulling us and thousands of other galaxies in that direction. Now, here's where things get even more interesting. In 2017, astronomers identified another major influence on our motion, the dipole repeller. This isn't a massive object pulling us. It's the opposite, a vast underdense region, a void containing very few galaxies. Because gravity attracts matter toward dense regions, voids effectively push matter away. Imagine a landscape with hills and valleys. A ball placed on a hillside rolls down pulled by gravity toward the valley. But if you think about it from the valley's perspective, it looks like the low-lying area is attracting the ball. Similarly, if you're near a void, the lack of gravitational pull from the void, compared to the pull from dense regions on the opposite side, creates a net force away from the void. You're being pushed more than pulled. The dipole repeller is located about 700 million light-years from us in the opposite direction from the Shapley supercluster. It's an enormous void, a region where galaxies are scarce. The combined effect of the Shapley supercluster pulling us and the dipole repeller pushing us accounts for our observed velocity of about 600 kilometers per second. We're caught between a cosmic pull and a cosmic push, flowing along with the large-scale currents of matter shaped by gravity over billions of years. Let's put this in perspective. The Great Attractor region lies about 250 million light-years away. The Shapley supercluster is about 650 million light-years away. Light from these structures has traveled for hundreds of millions of years to reach us. When that light was emitted, Earth was in the Triassic period. Dinosaurs were beginning to diversify, and the supercontinent Pangaea was just starting to break apart. The gravitational influence we feel today comes from the mass distribution, as it was hundreds of millions of years ago. By now, those structures have evolved. Galaxies have moved. Clusters have merged. but the information about their current state hasn't reached us yet. We navigate the universe using old maps, gravitational charts drawn by matter distributions, from a time when our planet looked utterly different. These large-scale flows aren't unique to our region of the universe. Everywhere astronomers look, they find galaxies with peculiar velocities motions that deviate from the smooth Hubble expansion. Some galaxies are falling toward nearby clusters, others are being pulled by distant superclusters. The universe isn't expanding uniformly, it's expanding on average, but locally gravity creates eddies and currents, pulling galaxies together, even as space itself expands. The competition between expansion and gravity shapes the evolution of cosmic structure. In dense regions, gravity wins, pulling galaxies together into bound clusters. In voids, expansion wins, stretching space and making voids even emptier. Now, let's talk about galactic collisions, because gravity doesn't just pull galaxies toward distant superclusters. It also orchestrates collisions between nearby galaxies, mergers that transform the galaxies involved, triggering bursts of star formation, feeding supermassive black holes, and eventually producing new larger galaxies. The Milky Way and Andromeda, the two largest galaxies in the local group, are currently moving toward each other at about 110 kilometers per second. In about 4.5 billion years, they will collide. I say collide, but as we mentioned before, galaxies are mostly empty space. Stars are separated by vast distances, and during a galactic collision, very few stars actually hit each other. Instead, the galaxies pass through each other like ghosts, their stars mingling, but rarely colliding. However, their gravitational fields interact strongly, distorting the galaxy's shapes, stripping gas and dust from spiral arms, triggering shock waves that compress gas clouds and ignite intense bursts of star formation. Simulations of the Milky Way-Andromeda collision show a beautiful and chaotic sequence of events. The first pass-through occurs about 4.5 billion years from now. The galaxies approach their outer regions, reaching toward each other, spiral arms stretching like reaching hands. As they interpenetrate, tidal forces pull long streamers of stars and gas away from both galaxies, creating bridges and tails of material. The collision compresses gas clouds and star formation rates surge, perhaps increasing 100-fold. Bright blue stars form in the disrupted regions, and the collision may trigger active galactic nuclei as gas funnels toward the central supermassive black holes of both galaxies. After the first pass, the galaxies separate briefly, their relative velocities slowed by gravitational drag. Then they fall back toward each other for a second collision. Over the course of about 1 billion years, the two galaxies merge completely, their stars and gas mixing, settling into a new configuration. The result is a single large elliptical galaxy, sometimes called Milkomeda. The beautiful spiral structures of the Milky Way and Andromeda, the delicate arms and dust lanes, are destroyed, replaced by a smooth elliptical distribution of stars. Most of the gas is either consumed in star formation during the merger or heated and expelled. The new galaxy is red, dominated by old stars with little ongoing star formation. It's the graveyard of two spiral galaxies, yet also the birthplace of a new elliptical galaxy, perhaps containing 1 trillion stars. What about our solar system? During this collision, will Earth be destroyed? Almost certainly not by direct stellar collision. The probability that another star will pass close enough to Earth to disrupt our orbit around the Sun is vanishingly small, perhaps less than 1 in a billion. However, the Sun's orbit within the Milky Way will be drastically altered. Currently, the Sun orbits the galactic center at about 230 kilometers per second, taking about 225 million years per orbit. After the merger, the Sun's orbit will change, perhaps becoming more elliptical, perhaps taking it farther from or closer to the new galactic center. Earth will continue orbiting the Sun, as it always has, unaffected by the galaxy's restructuring, but the night sky will look entirely different. Stars will be distributed differently. The Milky Way's band of light across the sky will be gone, replaced by a more uniform glow from the elliptical galaxy stars. Andromeda, currently visible as a faint smudge, will no longer be a separate object. It will be part of our galaxy. Galactic collisions are common in the universe. Hubble images reveal countless examples. Galaxies in the process of merging, their shapes distorted, their spiral arms twisted and pulled into tidal tails, their cores glowing with newly formed stars. The Antennae galaxies, about 45 million light-years away, are a famous example. Two spiral galaxies collided about 600 million years ago, and they're still in the process of merging. Long tails of stars and gas extend from both galaxies, flung out by tidal forces, resembling an insect's antennae, hence the name. Within the collision region, thousands of young star clusters have formed, visible as bright blue knots in Hubble images. Another striking example is ARP 220, a pair of galaxies in the final stages of merging. The collision has funneled enormous amounts of gas into the central region, triggering a starburst, an episode of star formation, so intense that stars are forming at about 200 times the rate they form in the Milky Way. The galaxy is one of the most luminous infrared galaxies in the nearby universe, glowing brightly in infrared light from dust heated by all the young stars. In a few 100 million years, the two galactic cores will merge completely, and the starburst will fade as the gas is exhausted. These mergers aren't just destructive, they're also creative. They build larger galaxies, mix gas, and trigger star formation, and may be essential for forming the massive elliptical galaxies we observe in the centers of galaxy clusters. In the early universe, galaxies were smaller and mergers were more common. The galaxies we see today are the products of countless mergers over billions of years. The Milky Way itself has likely undergone dozens of minor mergers, absorbing smaller satellite galaxies over its history. In fact, astronomers have identified streams of stars in the Milky Way's halo, remnants of small galaxies that were torn apart by tidal forces as the Milky Way consumed them. One of the largest is the Sagittarius dwarf spheroidal galaxy, currently in the process of being disrupted. Its stars are spread in a long stream, wrapping around the Milky Way, gradually being absorbed into our galaxy's halo. Have you ever wondered whether galaxies will continue colliding forever, or whether the expansion of the universe will eventually separate them so much that collisions become impossible? The answer depends on whether two galaxies are gravitationally bound to each other. If they are, gravity will overcome expansion, and they'll eventually collide. If they're not bound, expansion will carry them apart, and they'll never meet. In the local group, the Milky Way, Andromeda, and a few dozen smaller galaxies are gravitationally bound. They'll all eventually merge into a single large galaxy over the next few tens of billions of years. But most other galaxies we see, those not in our local group, are being carried away by expansion and will never collide with them. In fact, as expansion accelerates due to dark energy, galaxies beyond our local supercluster are receding faster and faster. Eventually, in hundreds of billions of years, they'll be so far away and receding so fast that their light will never reach us. The universe will appear empty except for the merged remnant of the local group. This brings us to a sobering realization about the future. The gravitational forces that have shaped the universe, that built galaxies and orchestrated collisions and created the cosmic web, are gradually losing their battle against expansion. Gravity can hold together structures up to a certain size, clusters and superclusters, but beyond that, expansion dominates. The universe is being stretched, and over cosmic timescales, the stretching will isolate each gravitationally bound group, leaving them as islands in an ever-expanding ocean of space. Yet within those islands, gravity will continue its work, pulling galaxies together, triggering star formation in their final reservoirs of gas, eventually exhausting all available fuel. Stars will die, and no new ones will form. Galaxies will fade, populated only by fading red dwarfs and cooling white dwarfs, and the occasional supernova, as a massive star remnant finally exhausts its last fuel. The universe's story, shaped so profoundly by gravity, will enter its final chapters, and the question of what that ending looks like depends on the ultimate balance between gravity and the mysterious force driving the universe's accelerated expansion, dark energy. We've traced gravity's influence from the curvature of spacetime around a falling apple to the flows of galaxies across hundreds of millions of light years. We've seen how it bent light during a solar eclipse, how it rings space-time like a bell when black holes collide, how it orchestrated the cosmic dance of planets and stars, how it revealed the presence of dark matter holding galaxies together, how it built the universe from near uniformity into the intricate cosmic web we inhabit today. But now, we must confront the ultimate question, the one that philosophers and physicists have pondered for centuries. What is the fate of the universe? Will gravity eventually win, pulling everything back together in a final cataclysmic collapse? Or will expansion triumph, stretching space until galaxies fade into darkness and isolation? The answer, as we've discovered in just the last few decades, is far stranger than either of those scenarios. The universe isn't just expanding, it's accelerating. Something is pushing against gravity, driving galaxies apart faster and faster. A mysterious force we've named dark energy that makes up about 68% of the universe's total energy density. And the battle between gravity and dark energy will determine not just the universe's fate, but the fate of every structure within it, from galaxy clusters to stars to atoms themselves. If you've stayed with me through this entire journey, exploring the deepest questions about reality, time, space, and the forces shaping our cosmos, thank you. If you found meaning or wonder in these ideas, please like this video and subscribe. These explorations continue, and your presence makes them meaningful. Let's begin with the discovery that changed everything we thought we knew about the universe's fate. For most of the 20th century, after Edwin Hubble discovered in 1929 that the universe is expanding, cosmologists debated whether the expansion would continue forever or eventually reverse. The question hinged on the universe's density. If there was enough matter, enough mass, enough gravity, the expansion would slow down and eventually reverse, pulling everything back together in a big crunch, the opposite of the Big Bang. If there wasn't enough matter, the expansion would continue forever, gradually slowing but never stopping, resulting in a big freeze where the universe grows cold and dark as stars exhaust their fuel and no new ones form. The boundary between these fates was called the critical density, about 10 to the negative 26 kilograms per cubic meter, roughly 5 hydrogen atoms per cubic meter, average across all of space. Astronomers spent decades trying to measure the universe's density and the rate at which expansion was slowing. The expectation was universal. Expansion must be slowing down, because gravity is always attractive. Mass pulls on mass. Even if the universe would expand forever, gravity should at least be slowing the expansion over time. The only question was whether it was slowing enough to eventually stop and reverse. In the 1990s, two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rice, set out to measure this deceleration precisely. They used Type 1a supernovae exploding white dwarf stars as standard candles. Type 1a supernovae occur when a white dwarf in a binary system accretes matter from a companion star until it reaches a critical mass about 1, 4 times the sun's mass, and undergoes runaway nuclear fusion, exploding with a brightness that's remarkably consistent. Because we know how bright they are intrinsically, we can determine their distances by measuring how bright they appear. And because their light is redshifted by the universe's expansion, we can determine how fast they were receding when they exploded. By comparing distances to recession speeds for many supernovae at different distances, astronomers could measure how the expansion rate has changed over time. Both teams collected data on dozens of distant supernovae, some so far away that their light had traveled for over half the age of the universe to reach us. They analyzed the data, carefully checking for systematic errors, comparing results. And in 1998, both teams announced their findings simultaneously. The expansion of the universe isn't slowing down, it's speeding up. Distant supernovae were dimmer than expected, farther away than they should be if the universe were decelerating. Something was pushing galaxies apart, counteracting gravity, causing the expansion to accelerate. The announcement was met with skepticism and astonishment. Accelerating expansion seemed impossible. It required something with negative pressure, something that exerted a repulsive gravitational effect, filling space and pushing it apart. Einstein had once proposed something like this: a cosmological constant, a form of energy inherent to space itself. But he later called it his greatest blunder after Hubble discovered the universe was expanding. Now, it seemed Einstein's blunder might have been correct after all. The universe contains a form of energy, dark energy, that doesn't dilute as space expands. As the universe grows more, space is created, and each new volume of space contains the same density of dark energy. Unlike matter, whose density decreases as space expands, dark energy's density remains constant, or possibly even increases. And this dark energy, whatever it is, exerts a repulsive gravitational effect, driving the accelerated expansion. In 2011, Perlmutter, Schmidt, and Reyes were awarded the Nobel Prize in Physics for this discovery. Since then, additional observations have confirmed accelerated expansion. Measurements of the cosmic microwave background surveys of large-scale structure observations of distant galaxies all point to the same conclusion. The universe's energy budget is approximately 68% dark energy, 27% dark matter, and only 5% ordinary matter. Dark energy dominates, and it's driving the universe's expansion to accelerate. So, what does this mean for the future? If dark energy remains constant, the universe will continue expanding forever, and the expansion will accelerate indefinitely. This scenario is called the Big Freeze or heat death. Over trillions of years, galaxies outside our local group will recede faster and faster, their light redshifted into invisibility. Eventually, they'll cross the cosmic horizon, receding faster than light, not because they're moving through space faster than light, but because space between us and them is expanding faster than light can traverse it. They'll disappear from view, and no information from them will ever reach us again. The observable universe will shrink, not because space is contracting, but because the accelerated expansion carries distant regions beyond our ability to observe them. Within our local group, now merged into a single large galaxy star formation, will continue for a while as gas is consumed, but eventually all gas will be exhausted. Stars will die, the most massive stars will explode as supernovae or collapse into black holes. Medium-mass stars like the Sun will shed their outer layers as planetary nebulae and leave behind white dwarfs. The smallest stars, red dwarfs, will burn for trillions of years, slowly exhausting their hydrogen, eventually fading to black dwarfs, cold, dark, and inert. By about 100 trillion years from now, the last stars will fade. The universe will enter the degenerate era, populated by stellar remnants, white dwarfs, neutron stars, and black holes, along with planets, asteroids, and drifting clouds of gas. Over even longer, timescales processes that are extraordinarily slow by human standards become significant. Collisions between stellar remnants, rare but inevitable, given enough time, will occasionally form new stars or trigger supernovae. Black holes will slowly evaporate through Hawking radiation, a quantum process where particle-antiparticle pairs form near the event horizon, one particle escaping, while the other falls in, causing the black hole to lose mass. A stellar mass black hole takes about 10 to the 67th years to evaporate. A supermassive black hole like the one at the center of our galaxy takes about 10 to the 100th years a googol to evaporate. Even protons, once thought to be stable, may decay, though the timescale is uncertain, possibly 10 to the 35th years or longer. If protons decay, then eventually all matter will disintegrate into radiation, leaving the universe as a cold, thin soup of photons, neutrinos, and gravitational waves expanding forever, cooling toward absolute zero. But that's only if dark energy remains constant. What if it doesn't? There are other possibilities darker and more dramatic. If dark energy's density increases over time, a scenario called phantom energy, the expansion could accelerate so rapidly that it tears apart bound structures. First galaxy clusters unbind as the expansion overwhelms their gravity. Then galaxies themselves are ripped apart. Then stars, then planets, then molecules, then atoms, then atomic nuclei, and finally even space itself is torn apart in a big rip. In this scenario, the universe ends not in cold darkness, but in a cataclysm where space-time itself disintegrates. The time scale depends on how fast dark energy's density increases, but estimates suggest the big rip could occur within 20 to 50 billion years if phantom energy is real. The universe has about 13.8 billion years of history behind it. In this scenario, it might have less than 4 times that much future ahead. Alternatively, if dark energy decreases over time, or if it's not truly a constant property of space, but rather a field that can change, then the universe's fate becomes unpredictable. Dark energy might decay, releasing its energy into matter and radiation, potentially reheating the universe. Or it might reverse, becoming attractive rather than repulsive, in which case the universe's expansion could stop and reverse, leading to a big crunch after all. The universe could collapse back into a hot, dense state, possibly bouncing and creating a new Big Bang, a cyclic universe that expands, contracts, bounces, and repeats indefinitely. These are speculative ideas not currently supported by observations, but they illustrate the deep uncertainty surrounding dark energy and the universe's ultimate fate. Now, let's consider what happens to gravity in these scenarios. In the Big Freeze, gravity continues to operate locally, holding together bound structures like our merged local group galaxy. But on larger scales, it becomes irrelevant. Expansion carries everything else away. Gravity loses the cosmic battle confined to ever smaller islands of matter in an ever-growing ocean of space. In the Big Rip, gravity is not just defeated, but destroyed. As expansion accelerates to infinite speed, space-time itself unravels in gravity. The curvature of space-time ceases to have meaning. In a big crunch, gravity wins, ultimately pulling everything back together. But the victory is Pyrrhic, ending in annihilation. Let's also talk about one of the strangest ironies in cosmology. Einstein introduced the cosmological constant in 1917 because he wanted the universe to be static, neither expanding nor contracting. At the time, no one knew the universe was expanding. Einstein's equations without the cosmological constant predicted a dynamic universe either expanding or contracting, which contradicted the prevailing belief in a static cosmos. So, Einstein added the cosmological constant, a repulsive term that could balance gravity and keep the universe static. When Hubble discovered expansion in 1929, Einstein reportedly called the cosmological constant his greatest blunder, because if he'd trusted his original equations, he could have predicted the universe's expansion before it was observed. But now, it turns out there is a cosmological constant, or something very much like it, and it's one of the most important components of the universe. Einstein's blunder was in a sense correct, just for the wrong reason. He introduced it to create a static universe, but it actually exists and causes an accelerating universe. The history of science is full of such twists where ideas discarded as mistakes turn out to be profound truths, and certainties crumble under the weight of new evidence. There's also the humbling realization that we don't understand 95% of the universe. Dark matter, 27%, is invisible and known only through gravity. Dark energy, 68%, is even more mysterious, its nature completely unknown. We're like sailors navigating a vast ocean by observing only the tips of icebergs, unaware of the immense mass hidden beneath the surface. Ordinary matter, The stuff we're made of, the stars and planets and gas, is a tiny fraction of the cosmos. Everything humans have ever observed, every atom in every living creature, every star that has ever shone, accounts for only 5% of the universe's content. The rest is dark, invisible, enigmatic. Can you imagine explaining this to someone from a century ago? In 1925, astronomers didn't even know other galaxies existed. They thought the Milky Way was the entire universe. Now, we know there are hundreds of billions of galaxies we've detected. Gravitational waves, we've photographed black holes. We've discovered that the universe is not just expanding, but accelerating, driven by a mysterious energy we can't explain. The progress is staggering, yet so much remains unknown. We're still at the beginning of understanding the cosmos. Let me bring this back to you lying here contemplating these vast time scales and cosmic fates. It's easy to feel insignificant when confronted with the universe's immensity, with time scales of trillions and googles of years, with the inevitability of stars fading and galaxies disappearing. But consider this. You are a pattern of atoms, assembled by billions of years of cosmic evolution, shaped by gravity pulling matter together, by stars forging elements, by planets forming by life, emerging and evolving and becoming conscious. You are the universe contemplating itself, a localized increase in complexity and awareness, a temporary eddy in the river of entropy. And while the universe's ultimate fate may be cold and dark, you exist now in this moment, able to understand and appreciate the beauty and strangeness of reality. Gravity shaped your existence. It pulled together the gas cloud that became the solar system. It holds Earth in orbit around the sun. It holds you to the ground. It guided the evolution of stars that created the elements in your body. It organized the universe into structures where life could emerge. Without gravity, you wouldn't exist. And now, through science, through patient observation and careful reasoning, you can understand how gravity works, what it is, how it shapes the cosmos. That's extraordinary. For billions of years, matter existed with no awareness of the laws governing it. Now, here you are, a conscious part of the universe, understanding the forces that shaped you. The future may belong to dark energy, to expansion and isolation and fading stars. But the present belongs to us, to awareness, to curiosity, to the joy of understanding. And perhaps that's enough. Perhaps the meaning isn't in the destination, not in the universe's ultimate fate, but in the journey, in the moments of wonder, in the connections we make with each other, and with the cosmos that created us. Gravity, the weakest of all forces, the gentlest curve of space-time, has been our guide through this exploration. It revealed itself through falling apples and orbiting moons, through bent starlight and ringing space-time, through the hidden mass of dark matter and the motions of galaxies. It built the universe from simplicity, sculpted stars and planets, enabled life. And it will continue shaping the cosmos long after we're gone, pulling together what it can, fighting against expansion, holding islands of matter against the tide of dark energy until even it can no longer resist the stretching of space. Thank you for spending this time with me, for following this journey through space-time and the nature of gravity itself. I hope you found moments of wonder, perhaps learned something that changes how you see the universe, maybe even discovered a new appreciation for the invisible forces shaping reality. These explorations will continue, and there are more stories to tell, more mysteries to unravel. If you've enjoyed this, please stay with us. Subscribe so you won't miss what comes next. And until then, rest well knowing that you're part of this vast, strange, beautiful universe held together by gravity's gentle hand, floating through space-time on a journey that began 13.8 billion years ago and continues still, moment by moment, breath by breath, into an uncertain but endlessly fascinating future. Good night.